Okay. Okay, good morning, everyone. Welcome to NITEX. Yeah, some of you have been here before. Some of you are here for the first time in our new NITEX headquarters. So my name is Francesco Petruccione. I'm the director of NITEX. Yeah? And instead of being at the beach this morning, I decided to come and welcome you because I'm still on leave until Monday. Yeah? But from Monday onwards, I will spend more time with you. Today I still have to, I promised my wife I would fix something at home before the end of the holiday. If I don't do it today, it won't happen, and I will be in deep trouble for the rest of the year. Anyway, there were three things that I wanted to mention, plus half a thing, not just for me to remember what I want to say. First of all, you all know NITEX is a fairly new kid on the block of research and training in South Africa. Yeah, we are a national, one of the first national research institutes according to the new National Research Facility Policy of our Department of Science, Technology and Innovation. We were born out of MITP, which was the previous National Institute for Theoretical Physics. But somehow, sometimes, you know, if you can't survive small, you have to survive big. Yeah, and that's why NITEX was born. So we are no longer theoretical physics. We're also astrophysics, which was partially already within NITEP. Yeah? The borderline is quite flexible there, but also mathematics, statistics, data science, quantitative biology, and bioinformatics, climate change modeling, and quantitative finance. Yeah, so we are a big family. Yeah? And today is the beginning of this new joint operation between NITEX and the Theoretical Physics Institute at WITS to keep the tradition of the Chris Engelbrecht School of Theoretical Physics alive. Yeah? The Chris Engelbrecht could go back to the 80s, yeah, and I think with very few exceptions, it kept we kept it alive regularly every year, yeah, and some summer school had speakers that a few years later became Nobel Prize winners, yeah. So good luck to you as well, to those of you that speak, yeah? And to those of you that maybe need a little bit longer to reach that level, yeah? But hopefully we will produce some of those. Yeah? So it's really nice that we keep this tradition alive. But of course, we didn't need text. Now we also need to try to start more summer schools also to satisfy the other disciplines. And as soon as the budget permits, we will start the process as well. Yeah? You know, I mentioned NITEX is now a big operation. Yeah? We have around 400 research associates scattered across all universities in the country. Yeah? Because we are a consortium of all universities in the country. Stellenbosch is the hub. But we have a node in Gauteng, hosted by WITS. We have a node in the Western Cape, hosted by UCT, one in KZN, one across the Eastern Cape and the Free State at Nelson Mandela University, and the sort of northern provinces at Northwestern University. Yeah? So the question is, you know, you have so many people, so many institutions involved, so many disciplines. How do you make one institution out of it? Yeah? And the only way, and that's what we, at least that's the philosophy, yeah? And I hope to get the buy-in from all of you, yeah, is that we need to focus on solving big problems together, yeah, regardless of the discipline in which we're working on. Yeah? You know, there are these big challenges that are more specific to one discipline than the other. Yeah? For instance, it would be nice if after this workshop, we would know what dark matter and dark energy is. That would be very nice. Yeah. But there are also other challenges. I think just about climate change. Yeah, climate change modeling. Yeah, it's not just a specific discipline-specific topic, yeah, because it involves input from physics, from data science, from machine learning, from mathematics, from statistics, essentially from finance, yeah, because there's also the economical aspect of it. Yeah. So those are the kind of the challenges that we would like to focus on solving big problems together. Yeah, and that is important not only because we want to make an impact. It's also important because we want to secure the flow of financing. Yeah, and if we don't show that we solve something, yeah, that is useful for society, yeah, and for South Africa, Africa, and the world, yeah, it will be very difficult to convince the powers to be to give us more funding to do the fun things that we want to do. Yeah, so far, we started pretty well, yeah, but we need to continue on the right trajectory. Yeah? And unfortunately, impact is what the guys that have the big fat wallet want to see. Yeah, so it's really important that we keep in mind that we want to work together across disciplines, across universities to achieve some goal. Yeah? What I noticed now in the last couple of years, some disciplines are better than others in digesting this philosophy. Yeah? Some people are better than others. Yeah? But I think it's an effort that we need to do all together. Yeah? And you being here is part of this. Yeah? So again, welcome to Stellenbosch. Yeah? And enjoy the school and the workshop. Enjoy also the surroundings. I think on Sunday you have free time, and on Saturday also a little bit. Yeah, so the weather is good. The wine is also good. Yeah, so enjoy the surroundings. The last half thing that I wanted to say, you probably saw where this is not so big. So the bathrooms are easy to find. You go out left, and there are two emergency exits. Yeah, one at the end of one corridor and one at the other end. I hope we don't need to use them. Yeah, but it shouldn't be difficult to find them. Having said that, Joao, thank you very much for organizing this. And I wish you good luck, and I will see you again on Monday.
And let's see if we can see you again. Use this if yeah. Okay, thank you. I'm used to teaching classes of 200 students, so I don't expect to need a microphone, but I'm sure that's okay. All right, so my name is João Rodrigues. For those who do not know me, I was, until the end of 2024, the director of the Mandelstam Institute for Theoretical Physics. I'll explain a little bit what it is. The current director is Kevin Goldstein, but he unfortunately wasn't able to come. So he asked me just to give a few introductory remarks and, of course, also welcoming remarks. So what is the Mandelstam Institute for Theoretical Physics? It's a university recognized institute, so it's not a national institute like NIFEX. And he sits within the University of the Witwatersrand up in Johannesburg. And we normally call the University of the Witwatersrand just WITS. So it's a WITS University Research Institute. As the name indicates, it carries a number of research activities in theoretical physics, namely theoretical high energy physics, as well as condensed matter physics. Now, over the years, it has hosted a number of workshops and conferences. We started off with what was called the Joburg series of schools in string theory that were originally hosted at WITS, University of Pretoria, but now more recently at the WITS rural facility next to the Kruger Park. But in 2014, when we became an institute, we started what were called the Mandelstam series of schools and workshops. And interestingly enough, we decided to move location from the north and started to host these in Durban. So we hosted a number of these Mandelstam meetings in Durban until COVID hit. And after that, then we've been kind of moving around a little bit, Pilanesberg, back at Wits. And this year, we thought that it would be a good idea to bring together a traditional summer school, the Chris Engelbrecht Summer School, together with one of the Mandelstam Institute's workshops. I wanted to mention a couple of things. First, the question is normally asked, why Mandelstam Institute? I think hopefully every one of you knows the name Mandelstam. Anyone who study ST and U channels and particle scattering know it comes from him. But more important, but in addition to that, he has made seminal contributions in quantum field theory and in string theory. So what is the relationship and the relevance to the University of the Witwatersrand, to Wits? Well, it turns out that he was a graduate of Wits University in the 50s. And in 2014, he agreed to have his name bestowed on our institute. So that is, for those who are wondering, what the source of the naming is. Concerning the Chris Engelbrecht School, it turns out actually that one of the first few Chris Engelbrecht School were held in 1994 at Storms River mouth in Tsitsikamma. And remarkably, there's still 2 or 3 survivors of that school, myself, Antal Yevitsky, and Robert Demelokov, who was a student, and will hopefully be coming later. So there is a long tradition of joint initiatives going back many years. So I think this is all I wanted to say. Welcome you to this summer school and workshop. I hope you enjoy and benefit from it. But before I finish, and because some people come, others go, and so on, I wanted to immediately thank the 2 real organizers of this meeting. One is Farah Samuels, the lady who's there. He really essentially put everything together, and I'm sure that you will all have received correspondence via email. And then Enosh Joseph, who did a lot of legwork. And of course, the staff of NITEX here in Stellenbosch, they are not here at the moment, but I wish to formally thank them for their support. I don't know, Farah, if there are any logistic aspects that you want to mention. The exits have already been mentioned. A lunch will be served just next door. And as Francesco has indicated, if you're welcome to walk around, this is a university town. It's very pleasant. But then we will take it as we go along through the program. Okay, thank you very much. And I hope you're enjoying it. Okay, I've been asked to be the chair for the morning. So the first speaker is Di Pietro.
Yes. I will use the whiteboard.
So you can actually turn the tablets around.
I think it's going to be also shown here, but maybe I will just need some space to move. Hey, can you hear me? Is it functioning, the microphone? Okay, great. Can you hear me? Is it okay?
Yes. Okay.
Okay, so this is Day2, so then starts.
Okay, thanks a lot. It's an honor to be here and to start this school. So let's see. Maybe I'll wait until you can see the whiteboard from there.
You now want us to rotate the table?
Well, you can choose. Maybe I don't know. Do you feel like you want to rotate maybe and look directly at the whiteboard, or just that maybe I'm gonna hit you when I move? I tend to move a lot. Thanks.
We should make
Okay.
space for you now.
Yeah, maybe can I rotate this? All these tables move, so. Oh, thanks. This one. Maybe. Okay. But you can use the table if you want. Just. Okay. Is it fine like this? Is everybody comfortable? Okay. So I will not erase the password and just put it in a box. So I'm gonna give you 2 lectures on the topic of let's say here, quantum field theory in anti-de Sitter space. So let me just give you, let me just tell you what is the plan of these 2 lectures. So today I'm gonna start some introduction, motivation, hopefully explaining what these words mean. And then I will start with some basics, some kinematical aspects. Aspects. Is it visible? Okay. And then, okay, I don't know if I'm going to respect, if I'm going to be able to finish everything, but the idea is that tomorrow I will show you some applications. Okay, in particular, I would like to discuss 2D sigma models. What did I forget? Okay, and so please, I mean, I need to gauge a little bit the level of the audience. So at any point, interrupt me for questions. Okay, let's make it interactive. It's more fun for everybody. Just let me already tell you a reference that you can use to read a bit about this topic. I mean, there is no reference which is a review strictly on this topic of quantum field theory and Sitter space, but a good pedagogical reference that covers many of the things I'm going to say are the essay lectures by Joop and Adonis on the essay lectures on the DSCFT. Especially the beginning, there are some sections which are specifically on quantum field theory and Sitter, and uses basically the same language I'm going to use. Okay, so unfortunately, given the time, I will not be able to cover the background on conformal field theory that I'm going to use. So I'm going to assume a little bit of familiarity with conformal field theory language. If you have never studied conformal field theory in higher than 2 dimensions, a good resource to start reading about it are these lectures by Lavarichkov called EPFL lectures on CFT in the larger or equal to 3 dimensions. Okay. Okay, so let me start. Of course, as I said, interrupt me at any point if you have questions. So what's the topic I want to cover? I want to cover some recent line of research that has the goal of using the background of anti-de Sitter space, so Euclidean anti-de Sitter space, which is basically hyperbolic space, okay, as a way to study the dynamics of strongly coupled quantum field theory, okay? So the geometry, the non-trivial geometry is used as a tool to understand aspects of the quantum field theory. So perhaps many, if not all of us, are familiar with the idea that anti-de Sitter is an excellent background to study quantum gravity, right? It's perhaps the background in which we understand best quantum gravity. And it sounds kind of natural that, so if it works so well for quantum gravity, maybe why not try to use it also to study complicated quantum field theories? Okay, so that's the, if you want, very broadly, the philosophy. And so let me give you some more detailed motivations. So these are going to be at this point a little bit sketchy. So if you don't understand all the details, it's okay. Then we're going to give more details as we go. So let's start with some motivations. Why you want to study quantum field theory in this background quantum de Sitter space? Okay. So our first motivation is that anti-de Sitter provides us with an IR cutoff. Okay. So what do I mean by that? So the typical problem that we face when we study quantum field theory, typical kind of question, is that we have some description of the dynamics at microscopic scales. So we write some Lagrangian that tells us how the fields interact at UV, like at small distances. And then often, however, we face the problem that when we go to larger distances, we go to smaller energies, the couplings become strong, okay? So that's, for instance, the case in non-abelian gauge theories like QCD that we use for particle physics, okay? So typical problem in quantum field theory is the energy scale. We have some definition of our theory in the UV, some microscopic definition, and then as we go with the RG flow, at some point we hit some, or let's say that we deform with some coupling G. Okay, we have some coupling G that deforms our UV conformal field theory, and then there is some scale lambda associated to our coupling, which is a strong coupling scale. Meaning that we lose control when our energy is of order of the scale lambda, we lose perturbative control. Okay? We cannot do perturbation theory anymore, and we don't know how to compute. Now, what do I mean by saying that ADS gives us an IR cutoff? So if we put our quantum field theory in a box of size L, okay? So let's say you take your theory and you study it, instead of studying it in infinite flat space, you decide you put your fields, you confine them inside some box, okay? What do you gain out of it? Well, what you gain is that now you have a new dimensionless parameter. Okay, which is your strong coupling scale times the the size, okay? So for instance, this you can think of this, maybe in the example you're familiar with, this would be lambda QCD, the QCD scale, or the scale of the young means, and you can form this dimensionless combination, okay? So now this is a new parameter that you have. And when this parameter is small, you can actually do perturbation theory. Okay, and then you can use it to interpolate between weak coupling and strong coupling. Okay, so you have a new handle in your quantum field theory that you didn't have before. Okay, so you can even hope that maybe there is no phase transition in between, so you can compute an expansion in this parameter and try to extrapolate to strong coupling to learn something about the dynamics of the theory. Okay, so in physics, we always like when we have some new dimensionless parameter, and here we gain one, okay, just by putting the theory in a box. Of course, this is not at all specific to anti-de Sitter, okay, so in anti-de Sitter, this will be the curvature radius, this radius L, okay. The curvature radius will provide some scale L that we can use in this way. But this is not at all specific, okay? This you can do with any type of box you like. And for instance, if people study quantum field theory on the lattice, that's what is always done, right? When you try to simulate a complicated quantum field theory using a lattice simulation, you're going to put it on a periodic box, typically, right? Because you need to have a finite volume. And also the finite volume of when you put the theory in the lattice also provides you some scale similar to this. So one can say, okay, but then why do you insist on ADS? You can also put it on, I don't know, a torus. So the advantage, that's going to be my second motivation. It was the first.
I ask a very basic question.
Yeah.
Maybe it's to me it sounds like a stupid question, so please tell me.
Please.
So if lambda times L is small, doesn't that mean that you have a UV cutoff, say like a lattice scale, and that means that the size of your box is smaller than your cutoff scale?
But this lambda is not the cutoff, is the energy scale at which the coupling becomes strong, okay? So for instance,
so it's a small end.
It's like more when you lose control in the IR, okay? So I'm just saying that, for instance, take the example of QCD. If you use a box which is much smaller than the scale of lambda QCD, then you're going to see gluons and quarks, which are kind of free, and you can use perturbation theory. Okay. Okay, but then why don't we use just an ordinary box? Well, we don't use an ordinary box. The reason why we like ADS more is because it's a very symmetric box, okay? So, of course, we all know that in infinite flat space, I'm going to be always Euclidean in this set of lectures, so there is no time. In infinite flat space, we have this kind of space-time symmetry, okay? In the dimensions with this number of generators, okay? Which is just the isometries of the infinite flat space. And then if we would use a periodic box, what is a periodic box? It just means that we take a circle of radius L to the D, okay? We take each dimension, we periodically identify it, and becomes like a D-dimensional torus, okay? But you see, this is a much smaller symmetry. It is only symmetry, which is, the only isometry we have here, okay, maybe there are also some permutations, some discrete ones, but the continuous one is just rotations of all these circles separately, right? So this is a much smaller one. We just have an SO2 to the power D. Okay, so we only have D generators. So if we want to do things in a finite volume in the simplest possible way, we lose a lot of symmetry. However, if we consider this kind of finite box, which is a finite box with curvature, then we just get basically a deformation of this symmetry here that we have in infinite flat space. Symmetry becomes SO1D. Okay, so this is the group. I will explain why. It's not supposed to be. I didn't even define yet what is a DSD, but just follow me for a second. And in this case, we have the same number of generators. Okay. So basically, we don't lose, even though we put things in a box, we don't lose any symmetry. Now, you could still complain that, okay, why do you insist on this ADS? This you could also do it by putting your theory on a sphere, on a d-dimensional sphere, okay? So I could put my theory on a d-dimensional sphere, and then I would have SO d+1 symmetry, okay? This would be, again, the same number of generators, okay? Oh, but there is also a reason why I like more hyperbolic space compared to a sphere. And so that's going to be my third motivation. The reason why I like more hyperbolic space is because, importantly, even though it's a box, it's a bit of a weird box. It's a box with an infinite volume. Okay? So it is true that studying our theory on ADS, we introduce this kind of IR cutoff. All the fluctuations are effectively cut off at the scale of the curvature radius of ADS. However, unlike a sphere, ADS has infinite volume, which means that many interesting phenomena in quantum field theory that rely on the existence of a finite volume can be studied on this background, while they cannot be studied on the sphere. I'm thinking about, for instance, symmetry breaking, spontaneous symmetry breaking. Phase transitions. And these concepts are, of course, very much related. All of these things that require somehow to change what happens to the value of your fields at infinity, okay? So you see, I'm already using the word at infinity. So I wouldn't know how to discuss those things if I study my theory on the sphere. While if I study my theory on hyperbolic space, this makes perfect sense. I just can look, for instance, at what my scalar field does at the boundary of ADS, and I can change the bev depending on various parameters, and this is going to change the phase of the theory, okay? Okay, so these are three strong motivations that corner me to this background as the most interesting, okay? So that's why I want to study quantum field theory on ADS space. I just want to mention, so I forgot something. So this infinite volume has an aspect which is related to it, which is the existence of asymptotic observables. So what do I mean by that? So in flat space, what do we like to study in quantum field theory? We like to study scattering amplitudes, for instance. Now, that's one of the most basic things. So we take particles, they arrive from infinite distance, then they meet each other in the center of our space, they do something, and then they go to infinity, okay? And then we study the amplitudes for this process. Now, if I would put my theory on, for instance, the sphere, I wouldn't have a direct analog of this, right? Because everything would take place in this small volume, confined volume. In ADS, instead, I do have an analog of that. So ADS as we will discuss in a moment in more detail, it looks a bit like the inside of a ball, but the inside of a ball with the property that as you approach the boundary of the ball, there is more and more geometry as you go, okay? So actually the distances are 2 points here are further and further away compared to 2 points more closer to the center, okay? So you should imagine that there is infinite amount of geometry as you approach this boundary of the ball. And here there is a very natural set of asymptotic observables which are obtained by putting local operators. We can study correlation functions of local operators inserted at this conformal boundary. Correlation. I mean, if you studied ADS-CFT, you're very familiar with this concept. So in ADS-CFT, that's what we actually the observable that we use. No, when we do quantum gravity in anti-de Sitter space, we precisely say that the observable are correlation functions at the boundary. I'm just saying that this makes sense also for a quantum field theory in anti-de Sitter. If I have a quantum field theory in anti-de Sitter, I can study correlation functions at the boundary. And they're a bit analogous to this matrix on flat space. Okay, they're analogous to as matrix amplitude in flat space. And the very nice property is that they are covariant under this symmetry SO1D. So they are like correlators in a D-1 dimensional CFT. Okay? So they have the same symmetries as correlation functions in a Euclidean conformal field theory in D-1 dimensions. Okay, so this was like the sketchy motivation of why I like quantum field theory in anti-de Sitter space. And now, if you don't have questions, I will move on to a bit more details.
So one question.
Yes.
In your first motivation, this perturbative parameter also will exist when theory becomes strongly coupled in the UV, right? Or is it only true for asymptotic free theory?
Well, I have in mind the setup in which the theory is weakly coupled when IDS is small, and then we try to understand what happens when IDS becomes larger, okay, which we go to flat space. You could ask also the opposite question. You could consider a setup in which you know very well the IR. Actually, typically that's what we do in a sense in holography, right? So we know very well what happens when IDS is large, and then it's a bit mysterious what happens when we take IDS small. But yeah, so far people have studied more this case in which you know very well the macroscopic, at least in quantum field theory, people study the case in which you know very well what is the macroscopic definition. And then, so in this sense, it's more similar to the philosophy on, of like, I don't know, putting your theory on a lattice, right? So you know very well the macroscopic definition, and you want to see what properties emerge when you take the background to be large, and you go to large distances. Okay. So start a little bit with any other question?
Are you interested in normal cavity or also supersymmetric?
You can also study supersymmetry.
That's another argument for ADS.
Yeah, absolutely. Yes, I mean, of course, for instance, if you put a theory with four-dimensional theory, let's say, I mean, what I want to say is that the boundary is going to break some of the supercharges. So For instance, if you want to have some holomorphy left, let's say for dimensions, you have to start at least with n equals 2 in the bulk. So that you're going to have 8 supercharges, but then the boundary breaks it to 4. Instead, if you start with n equal 1 in 4D, you're going to end with the same amount of supersymmetry as 3D n equal 1. It's a bit more complicated. But yeah, for 4D n equals 2, for instance, in anti-de Sitter, you can use localization. Okay. So now let's do some introduction to PDS in more details. Okay. So far we just were very sketchy. So one of the most confusing aspects of this is to not get confused between the boundary dimensions and the bulk dimension. So I'm going to call it ADS D plus 1. Okay. So D is the dimension of the boundary. So I'm always going to consider the Euclidean geometry. So it's the same as hyperbolic space. Okay. And I like Poincare coordinates, so let me just define the geometry, this particular set of coordinates, then we're going to give a more abstract point of view. So one way to cover this space is with this set of coordinates called Poincare coordinates. Z and X. Z is a positive real number. X is a vector in Rd. And this is the metric. So here in front there is this L, which is the curvature radius. Okay, and the way it looks, this planar boundary at z equals 0, and this is z, and these are the x directions. Okay, so you can slice it with planes at each z. And okay, so you see what's going on is that since we have this factor in the metric, distances get rescaled as we approach this z equals 0 boundary. Okay, and the metric as a divergence at this boundary. Okay, so this is not really, you shouldn't really think of this boundary as part of the geometry. It's what is called the conformal boundary. Okay, because the metric is not really defined here, only the conformal structure is defined. And this conformal boundary is like morphic to RD. At least it's clear in these coordinates we are using. So this is a maximally symmetric space, which means what we said before, the number of generators is the same as a flat space in the same dimension, and it has a constant negative curvature. Okay, so you can compute the Riemann tensor, and you see there is the maximally symmetric form, which is just in terms of products of G's of the metric. It's convenient to, having defined it like this, it's convenient to view it as a hyperboloid. In this picture, it's not super manifest what are the isometries. We can make it more manifest if we view it as a. I realize that this part is not.
I can't see the black properly. Not sure it's one of the audience members. So I asked maybe to use blue.
Okay, sounds good.
So what you see there is not what they see. They see that, but it's obviously compressed for Zoom standards.
Yeah, no, but also realize now that this part is not showing.
Oh.
But I don't know if it's a good idea. I can also just decide to use this part.
Then the people online has a little bit more definition.
So I will just use this part? Okay, good, let's do that. And I will use a blue. Okay. So let's, I was saying that we can view it as a hyperboloid in inside D plus 2 dimensional Minkowski space. So this is R1 plus 1. Okay, so this is D plus 2 Minkowski. Okay. So how do we do it? So we start with the Minkowski metric, which we're all familiar with. Yes. Plus the x1 third d plus 1. You get more visible, the blue?
They did give thumbs up, they didn't, looks like they reasonably look at it.
And then inside this space, we put a constraint. The constraint is like this, minus x0 squared plus x4 squared. Okay, in other words, if we use the Einstein notation, it is going to be xa equal minus r squared. Okay. And how does this look? This looks like this. We have x0. We have the other axis. There is a null cone. So, okay, so there is a null cone. And then what this constraint gives us is a hyperboloid. Okay, it sits here inside. And it's just to denote that you have all the directions around. Okay. So it turns out that this hypersurface inside the plus two-dimensional Minkowski is precisely isomorphic to this ADS D plus 1. Okay. You can kind of see from this picture there's going to be Euclidean geometry, you see, because it's transverse to the time direction. So there are only space directions as you move in this surface. And this is the surface that we are going to put our quantum field theory on. And our ADS is this. Let's say 1 squared. Also going to be useful to parameterize the null cone. So the null cone that satisfies this equation. Okay, so the square of the vector is 0. So there is the null cone. Now, why is this picture nice? This picture is nice because it makes manifest the symmetry. Okay. Yes. Because if you act with any Lorentz transformation in the D plus Minkowski space, it's kind of clear from this constraint, right, that this hypersurface is going to be left invariant, because you see this XAXA is invariant under Lorentz. And similarly, also the null cone is also invariant over these transformations.
Just give us 1 second.
Yep.
There we go. Oh. Well. Dat hij goed. Dat hij pracht. Ja, dus als je maar weer.
Okay, I can go. Okay, so for instance, you can write the Lorentz generators in Minkowski as this combination. And then if you plug in, you can choose any coordinates you want for this hyperboloid just by solving this constraint, okay? So you're going to find some form of the x's that you like that solves this constraint. If you plug it inside of here, you're going to get the generators of your isometry group acting on the hyperboloid, okay? So for instance, the Poincare coordinates that we saw before is this particular solution of the constraint. You choose this x naught. You can verify that the constraint is satisfied. X mu L over mu here goes from 1 D. And then you have to choose x d plus 1 b L 1 minus x squared minus d squared divided by 2z. Okay, so if you choose this particular form of the x's, you can verify, you can do this small exercise to verify that it satisfies the constraint. Okay, so it's a way to parameterize the hyperboloid, which corresponds to the Poincare coordinates we saw before. And then you can work out, by plugging it here, you can work out the form of the generators, okay? You're gonna recover the generators of the isometries acting on ideal space. Okay. Now, another thing that this picture does for us is that it gives us a way to understand the conformal boundary of ADS. Okay. So how do you think about, so you see in the Poincare coordinate picture, the conformal boundary is obtained by moving towards z equals 0, okay? And we have this plane which is at infinite distance from every point inside, is our conformal boundary. How do you see it from this picture? Okay, so we have this picture of the hyperboloid inside the one more dimensional Minkowski. So you can understand it like this. If you take a point on the hyperboloid, you try to move it to infinity. Okay, try to move to infinity in this hyperboloid. What this does, if you move to infinity in this hyperboloid, you single out some direction. Okay, you single out some direction. Let me draw it like this. Okay. So what you should think of as the points at infinity in your hyperboloid is in one-to-one correspondence with rays in this null cone. Okay. So let me write it here. So points at infinity is the same as rays in the null cone. Okay, so this suggests, it looks a bit more abstract than this, but now we're gonna map the two pictures. This suggests that we should think of the conformal boundary of anti-de Sitter as the set of rays in this cone. Okay. What is the set of rays? The set of rays is what is called projective null cone. Okay, so this means that conformal boundary. Where should I write it? Let me erase this. Boundary is given by the set of A's with up to the identification A is identified with lambda A. Okay. So if I do this identification, I'm basically describing just rays, right? Because I'm saying that 2 points are identified if they are obtained by rescaling by a positive number. So this is what is called projective null cone. And so I'm suggesting that we should think of the boundary of this hyperboloid as this projective null cone. And you might ask yourself, what does this have to do with the description we had before? Well, it turns out, I don't have time to describe this in details, but you can see it in the reference I gave you, and you can ask me later if you want more details. It turns out that this projective null cone precisely has the correct structure to encode flat space, d-dimensional flat space, up to conformal transformations. Okay, so I will now. So this is exactly the same as d-dimensional flat space, but not with a fixed metric, just with a fixed conformal structure. Okay, up to conformal transformations. So what does this mean? Let me try to make it a little bit more concrete. What does this cone, projective null cone, have to do with flat space up to conformal transformations? The idea is that when you want to describe a projective space, what do? Well, if you want to be concrete, you're going to pick some section, right? So you're going to intersect this with some manifold in such a way that you fix you have to gauge fix these identifications that we have, right? We can identify P with lambda P, but there is no unique way to do that. So, for instance, let me write a little bit better. So if we have this cone up to these identifications, one way we can describe it is by doing a section with a plane like this. Okay, so in this case, what do we get? We get a sphere. D-dimensional sphere, right? But another thing you can do is that you can intersect it, for instance, with a plane this direction. Okay, if you intersect it in a plane with a plane in this direction, you're going to get a different section. So a section that looks like this. Okay, and these different sections, and okay, this is in, I will show you in a second that this is one-to-one correspondence with just RD. This parabolic section is one-to-one correspondence with RD. And so the different sections of the cone are just different binary scalings of the flat metric. So the reason why I'm going through this is not just because it's a nice formal description, but if we manage to get there, using this description with the null cone and this embedding of the hyperboloid in a higher dimensional Minkowski makes it much easier to do computations. Okay, so it's actually also convenient for practical reasons, as we're going to see in a second.
You're missing one ray in the second section, right?
I am missing
One ray.
so this is a plane and it intersects along this line.
The one null ray, this ray. It's not intersecting with this.
So what I mean here is that this is going to be at some transverse dimension.
Yeah, but the ray directing this way, it doesn't intersect with this section, right?
Can you draw it? No, I don't understand what you mean.
This way.
Yes.
Is it okay?
Yeah. You mean that I don't get all the points of the null cone? Sorry, I didn't understand it. Yes. So, but that's yes. So we're missing something, and that is like the point of infinity, right? So usually when we describe flat space up to conformal transformations, sometimes we need to add points at infinity. Okay. So indeed, you see the sphere precisely captures all the points of the projected null cone, while this misses one point, as you correctly pointed out. It took me some time to understand, but we are familiar with the idea that indeed, when we do a rescaling from RD to SD, it is true that this guy contains one more point at infinity compared to this. So that's precisely the point at infinity that you're mentioning. Let me explain why this is the same as RD. So this intersection is, well, maybe in view of time, I can just tell you what is the parameterization. This is the cone. And if you want to recover the boundary in Poincare coordinates, you just need to choose 0 to be 1 plus x squared divided by 2. Then you choose these guys to be x mu. And you choose p d plus 1 to be 1 minus x squared divided by 2. Okay? And you can convince yourself, you see, what's going on here is that what constraint are we imposing? What is the constraint that defines this section? The constraint is that P0 plus PD plus 1 is fixed to be 1. Okay, so this is this plane that I'm drawing here. This is the plane P0 plus PD plus 1 equal 1. So I'm intersecting the cone with this plane, and the intersection gives me this parabola. And this parabola is in one-to-one correspondence with the boundary of ADS. Okay. Now, let me, in the time that remains, I want to explain why, using all this construction, why this is very powerful to actually constrain correlation functions. Okay. So we want to study a quantum field theory in this background, so we better be able to use all the constraints of symmetry in the most efficient way to actually reduce the functions that we need to compute to the simplest form possible. Okay, so are there questions about this before I move on?
And you have in mind of constraining specifically this boundary correlation functions?
Not just boundary, also bulk correlation functions, yes. We're going to discuss in a second. Yes?
I just want to follow. So if you have a horizontal section through the cone, you're basically picking out a sphere of different size, but I think I must have missed the portion about choosing a different plane on which you're intersecting. So I understand if you intersect the cone higher up, you get the sphere, but now if you intersect on an angled plane, now you get something which is, I don't know, would you call that a sphere still, or some kind of distorted thing?
You mean if I just I don't go full parallel, but I just move it a little bit. Yeah, that is also a valid section, and is going to be related to a conformal transformation, for instance, starting on the sphere. You see, these sections, so the null cone itself is invariant under SO1 D plus 1, okay? The sections are not each of them invariant. They're all invariant up to the projective identification. So if you act with SO1 D plus 1 on one particular section, you're going to get a little bit distorted section, for instance, and then you have to go back using the rescaling, okay? And that's going to give you a conformal transformation on the sphere. Yes?
Equation P0 plus PD plus 1 equals to 1.
Mhm.
It seems like it's missing more than 1 point of from the SD,
Really?
right? Unless it's very close. I mean, the right hand side of that equation is very small. You always miss more than large set of points on the infinity circle.
In terms of ray, I believe I should be missing only one ray. Maybe I'm only missing the one that is. I mean, we can work it out exactly which one is missing.
Yeah,
But
okay.
yeah. Okay. So let me tell you a bit about correlation functions. Okay. So now, yes, we are going to have bulk operators. And boundary operators. Okay. I want to study my quantum field theory in anti-de Sitter, so now I will draw it again as the inside of a ball. Maybe let's do it. Sorry, let's not. Let's use we stressed more Poincare. We have the possibility of inserting some operator inside, some operator in the boundary, okay? And so these I will denote just as O, some operator inside. This means inside. And the operators at the boundary I'm going to denote with a hat, okay? So it's convenient to use these embedding coordinates that we had before. So the bulk operator I'm going to write as O of X with X minus R squared. Well, the boundary operator I'm going to denote as O of P with E equals 0. Moreover, since this needs to be defined on the projective null cone, I need to tell you what happens if I scale. Okay? So all the boundary operators need to have some homogeneity property, which allows to define them on the projective null cone. So this homogeneity property is this form. Okay, and it enters this parameter delta, which is the scaling dimension of the operator. Okay, so now let's consider some correlation functions.
So by scaling dimension, you mean its eigenvalue under, let's say, the.
Well, at the moment I didn't give you an independent definition, so you can also take it like this, but yes, you can take this as a definition, but it turns out that if you work out the action of the conformal group in the way we mentioned before, this is going to be indeed the eigenvalue under the scale transformation.
Translations in Z. Is it,
Well, yeah, I mean, these guys are inserted here at the boundary, so you should really think about it as more like in terms of one particular generator of SO1 D plus 1, SO1 D plus 1, And this particular generator, yes, it's the same that in the bulk acts as in the bulk it acts as z goes to lambda z and x goes to lambda x. Okay, so this you can check its isometry. And okay. So let's start, for instance, a simple exercise is to ask, what about bulk one-point functions? Okay, so suppose I want to consider this. Okay, and now by isometries, this can only be a function of xa, okay, but this is actually just a number. Okay, immediately you derive that bulk one-point functions must be constant. Okay, this is not very surprising. It's just a statement that until the sitter is a homogeneous space, so every point looks like any other point. So if you have a bulk one-point function, it can only be a constant. Okay, so it's a bit boring, but okay. Then another kind of easy thing is a boundary two-point function. Okay, this is the usual result in conformal field theory. But in this language, how does it look? So by isometries, this can only be a function of P1 dot P2. Okay, it can only be a function of P1 dot P2 because P1 square is 0 and P2 square is 0. But then it also needs to satisfy this homogeneity property. Okay, so the only way to satisfy this homogeneity property is that it must take this form P1 dot P2 to the power delta, and it can only be non-zero. So let's say this was operator 1, and this was operator 2. It can only be different from 0 if delta 1 is equal to delta 2 is equal to delta. Okay, you can convince yourself that this is the only thing that satisfies homogeneity property, both for this operator and this other operator. Okay? Now, these two are very easy. Let's do something a little bit more complicated.
So like a boundary one-point function, would that be 0?
A boundary one-point function must be 0, yes, yes. So yes, so these are the simplest thing in a sense that are non-zero. Now let's do a bulk boundary two-point function. Okay, so suppose now you have your operator O in X and the bulk operator, a boundary operator in P. Okay, so now again, by the isometries, you see, that's the nice thing of this embedding coordinates is that it's very easy to implement the isometries, right? By the isometries, this can only be a function of X dot P. Okay, yes. But then on top of that, you need to satisfy the homogeneity property in P. Okay, and then there is not much this can be. It can only be 1 over X dot P to the power delta. Okay, there can be a coefficient, of course. That's an important thing. We call this coefficient usually like this, P O hat. Okay. Let me just give you the expression in Poincare coordinates. So it's customary to put here a -2. But okay, this is just a convention. Okay. Also here, actually, it's customary to put a -2. Again, convention. And in Poincare coordinates, this -2 X dot P is just Z squared plus X minus Y squared divided by L. Okay, try to do it. Try to work it out. Okay, so what do I mean by this? I mean that the boundary operator is in Y and the bulk operator is in ZX. And the correlation function must have this form. Okay, so again, this is completely fixed by the symmetry up to some number, completely fixed by the symmetry up to some number. Now to finish, let me just tell you an example of something that is not fixed completely by symmetries. Something that is not fixed completely by symmetry is a bulk 2-point function. Okay, so that's going to be important for us also tomorrow. Bulk 2-point function. So if you consider now O x1, O x2, okay, can also be two different operators if you prefer. Now here isometries just tell us that this must be a function of x1 dot x2, okay? But now this can be an arbitrary function of this quantity, okay? I cannot put x1 squared because x1 squared is fixed, is a constant, x2 squared is also fixed. You can also think about this if you prefer as the chordal distance, what is called chordal distance. So it's 1 minus x2 squared because it is just minus s squared, sorry, minus 2 s squared, minus 2 dot x2. So it's equivalent to use x1 dot x2 or to use x1 minus x2 squared. They're just equivalent invariants. Okay, so let's call this quantity some name. It's usually called zeta. And zeta in Poincare coordinates look like this. D1, D2. Okay? So now if you have, call it F prime. All that. If you have a bulk 2-point function, in general, it's going to be a non-trivial function of this single object, which is this chordal distance zeta. So you're going to have to compute a complete function of zeta. Okay, just this is like the first non-trivial thing. Let me also mention that we could also have gone on with boundary correlation functions, okay? So for instance, a boundary 3-point function, if you ever studied CFT, you know that it's again completely fixed by the conformal symmetry. It's completely fixed by the conformal symmetry up to what is called an OP coefficient. There is some coefficient that sits there. And the analog of this bulk 2-point function on the boundary, so the first thing that is a non-trivial function is the 4-point function, okay? So if you want to have something non-trivial at the level of boundary correlation functions, you have to consider 4 boundary operators, and then you have a function of 2 cross ratios, okay? So the more complicated things start appearing when we have 2 points in the bulk on where we have 4 points at the boundary. Okay.
What about combinations of 3 points?
You can also study that, but you can work out exactly what they depend on. I expect that perhaps if you have 2 points in the boundary and 1 in the bulk, maybe it's going to be still 1 invariant, but I'm not completely sure. But in any case, you can work it out. We are going to use more the bulk 2-point function. Okay, I can stop here.
So we have maybe 1 or 2 minutes for questions.
Yes.
Check the alpha minus 2.
Yeah, so what I did here is that I expanded this. So this, I mean, right, x1 minus x2a, x1 minus x2a. Then I expanded this. I get x1 squared plus x2 squared minus 2 x1 dot x2. But this is constrained to be minus L squared. This is constrained to be minus L squared. So eventually you get minus 2 L squared minus 2 1 dot x2. Okay. It's equivalent.
So you can take the limit where x1 and x2 are both on the boundary.
Yes,
There, but then your f should reduce to that 1 over. that.
precisely.
So f is still not arbitrary completely, it has to have the right
Yes.
homogeneity relations.
Well, what I was hoping to be able to discuss, but I didn't manage, is that, okay, so I said that in the boundary, the first object that is non-trivial is the 4-point function, right? And we are familiar perhaps with the idea that if we have a 4-point function in a conformal field theory, it can be expanded using what is called conformal block expansion, okay? The idea that you take operators pairwise, you fuse them, and you get an expansion as a sum of 2-point functions. So similarly here, what you can do is that you can do precisely what you said. You can take the two bulk operators and push them to the boundary. Okay? If you push them to the boundary, you get again an expansion in boundary 2-point functions. Okay? And you're gonna get for each primary that appears, there is going to be an analog of a conformal block. Okay, so this object here can be expanded in conformal blocks, each of which is associated to a particular primary of the boundary that appears in this, what is called the bulk-to-boundary OP. Bulk-to-boundary operator product expansion. Okay, so yes, but in practice, what this means is that when you go to the boundary, you see Z1, Z2 are going to 0, so this chordal distance is going to infinity. So the points approaching the boundary is the same as the point becoming very distant in the bulk. And then this object here needs to have an expansion. So in this limit, yeah, of course, as you were mentioning, the first power is going to be 1 over zeta to something, but then there is going to be all of a series of powers that can be resummed in a clever way.
Sorry, maybe a silly question, but these correlation functions, I mean, is this in a free theory? Do you have free theory in mind, or is this true also at any coupling?
Yeah, this is what we used so far in this discussion. So it was a bit abstract, but it's valid for any quantum field theory because we just use the symmetry, okay? So as long as it is allowed for my quantum field theory to be put on ADS background and to respect the isometries of ADS, which is kind of something that I expect for any local quantum field theory, at least with some appropriate choice of boundary condition, I expect it's going to be able to satisfy the isometries of ADS. Then these constraints need to be valid. Okay. Of course, they need to be valid also in free theory, and you can explicitly check all of these things in a free theory if you want.
Questions from online? Right, so then that's yes, sorry.
Okay, no, it was related actually. I mean, so thinking of ADCFT, right? I mean,
Mhm.
there's this weak, strong kind of thing.
Yes.
We're also interested in the boundary 2-point function,
Mhm.
but then we calculate using both the boundary propagators and
Mhm.
but then it's supposed to be a strongly coupled
Yes.
2-point function. Here, this is weak, strong, like your
Yeah,
all the theories are
so
weakly coupled, right? In the bulk and ground.
yeah, let me stress that. So I should stress that there are many similarities with holography, but it's also conceptually very different. So when I study a quantum field theory in anti-de Sitter, it is true that I can compute these boundary correlation functions. It is true that they satisfy all the constraints of conformal symmetry. However, I'm not claiming that there is some sort of duality, okay? I'm just saying that these are some observables of the quantum field theory, okay? Just like if I study a quantum field theory in flat space, I have this matrix, it's an observable of my quantum field theory. Here, these boundary correlation functions are some particular observable of my quantum field theory. They don't encode the full set of observables, just like this matrix is not the full set of, so there is no duality here. It's just I'm computing some observables, okay? And I'm not so far assuming anything about weak or strong coupling. So if the QFT is strongly coupled, it's going to be hard to compute this correlation function. If the QFT is weakly coupled, it's going to be easy to compute this correlation function. Okay? So there is no strong weak duality or anything like that.
All right, so let's thank Lorenzo there. Okay, so there is coffee next door and we start at 11.
I just want to quickly ask to Vicky, Basu and Rodriguez just to quickly chat with me just regarding your slides for later in the afternoon.
So the next speaker is Seoul National University, which is about very black holes in ideas.
Thank you very much for the introduction. Thank you very much, first of all, for inviting me to South Africa, Stellenbosch. It's my first time to visit this city. It's so beautiful. And if you have attended my talk before, you might have noticed my voice has slightly, not the 100% condition. And became a bit worse after 20 hours of flights and so on. So please forgive me about that. And today and tomorrow, I'll be talking about the following topics. Today, I'll be talking about the new black hole configurations in ADS spacetimes, the so-called hairy black hole configurations, which violate the no-hair theorem of black holes in a very interesting manner. Today, I'll try to present the configuration and discuss the gravitational thermodynamics and the gravitational Hilbert space problems and so on. Tomorrow, I'll be talking about a topic which is only halfway intersecting with today's topic. Tomorrow, I'll be talking about the general understanding of the black hole microstates, let's say the BPS black hole microstates, using ADS-CFT holographic correspondence. So I'll be presenting to you in the first half of tomorrow's lecture the general program of trying to better understand black hole microstates. In the latter half of my talk, I'll apply this general program to better understand these hairy black hole microstates. So the latter half of tomorrow's talk will have at least qualitative overlap with the talk today. So I'll be explaining to you these hairy black holes in ABS today.
Just click on your slides.
Okay.
Just click on it on the laptop. On the laptop. Just use your trackpad and just click on the slide. This with the mouse. On the laptop itself.
What?
Just click on your slides. Just
click
do
my slide.
Laptop trackpad. Just click on the slides.
Just do one left click.
There we go.
Thank you very much. So, in certain gravitational systems, another apology. I didn't know that this lecture will be vertically this long. So, apologies if there's somebody at the back have bad eyesight. So, I'll try to explain many things in words. So you have, let's see. Okay. So, in certain gravitational systems, simple gravity theory like Einstein-Maxwell theory, in which you have metric and electromagnetic fields, you can have certain black holes carrying mass and charge, and it may be rotating. But if you consider a situation in which the matter collapses to form a black hole with a horizon, and everything settles down into a stationary configuration, in some theories, a theorem called the black hole no-hair theorem has been established, which says that after the matters completely collapse and it takes a stationary limit, the black holes are characterized only by a few of its conserved quantities. And a lot of the other information about the collapsed matters, after they get absorbed by the black hole, they leave no hint, trace on the final stationary black hole solutions. So roughly speaking, we call this no-hair theorem. And the information about the absorbed matters, way more than these conserved quantities, is the very basic reason that the black hole information paradox has been posed. So this kind of no-hair theorems are satisfied in a class of gravitational theories coupled to certain matter fields. The interesting thing is that this theorem is sometimes very often violated in other more exotic gravitation, not exotic, but other more richer class of gravitational theories. You know, Einstein's gravity coupled to more richer class of matter, sometimes put in ADS, sometimes you go to higher dimension. This theorem is very often violated. And it's often violated by particular modes of matters within your theory, which want to develop more interesting structures outside the event horizon. If this kind of configuration exists, we call this configuration violating the no-hair theorem loosely as hairy black holes, having more hairs of the information of matters outside the event horizon. Today, among many possible hairy black holes that we know in various situations, I'll try to discuss the black holes in the anti-digital space-time background. One of the main motivation is that, of course, we have a better control on quantum gravity in ADS spacetime. We want to get a better understanding of the quantum physics of black holes, thermodynamics of this quantum gravitational system. Having these hairy black holes, these black holes have interesting implications about these fundamental questions of quantum gravity. Especially combined with topics like black hole thermodynamics and so on, I'll try to explain how this new hairy black hole provide a more interesting and complete view on the quantum gravity spectrum or the quantum gravity Hilbert space and so on. So I should first start the discussion by the simplest kind of situation. I'd like to first discuss a black hole in ADS which carries rotation. Namely, I'll start the discussion by studying the Kerr ADS black holes. General discussion holds in any dimensional ADS if it's higher than ADS 3. But for the simplicity, in the first part of my talk, I'll discuss the black holes in ADS 4. We consider Kerr black holes in ADS negative cosmological constant background in 4-dimensional ADS space. Let's first consider black holes with rotations, either in ADS background or asymptotically flat spacetime. What I'd like to emphasize first is if you perturb some kind of rotating black holes, either in asymptotically flat spacetime or in ADS spacetime, these black holes, if it experiences perturbation of particular sorts, it makes a very interesting reaction to the perturbation you have put in. And this is because the rotational black holes have a very interesting region right outside the event horizon, which is called the ergosphere. Okay? Roughly means a space-time region very heavily dragged by the black hole rotation. And the existence of this ergosphere region leads to very interesting energy extracting processes out of the black hole. Depending on the context, it's called by various different names. But in the wave picture, we often call it superradiance. It means the following. If you send in some waves into these ergo regions, and black holes can react to the input of waves you have sent in by reflecting some waves back. If superradiance happens in certain condition, due to some physics of ergosphere, it turns out that the outgoing amplitude reflected by the black hole can be bigger than the incident amplitude that you have sent in. So this leads to an energy extracting process called superradiance. More reflected waves than the wave you have put in. This way you can extract out some energy out of this black hole, rotating black hole. For asymptotically flat black holes, superradiance is just exotic reaction of the black holes to the finite perturbation that you have sent into the system. But if you consider similar physics in anti-distant spacetime, it creates a genuine instability of this configuration. Instability of a classical configuration means you make a small, very small perturbation, you wait for a long time, the configuration time evolves finite distance away from it. Okay? So the way it happens is the following. So you put in a small perturbation, there's a faint incoming arrow here, which is almost invisible. You send a very small perturbation of incoming wave. The superradiant black hole will send out a slightly amplified outgoing waves. But the antidistant spacetime, Lorenzo didn't really explain yet, but it's a gravitational box. Yeah, he said it's a box. It's a kind of place over a gravitational box, which turns the outgoing wave back to a new incoming wave. Okay? So it's a slightly amplified incoming wave, and it superradiates, and it just repeats until the outgoing wave, if you wait for a long time, becomes a finite distance away, a finite distance separated away from the original black hole configuration. So you make an infinitesimal, very small perturbation, wait for a long time, the superradiance and reflection repeats in ADS spacetime to make a finite deviation, signaling a genuine instability of the solution, or some similar to the tachyonic instability of the configuration, which is sitting on the unstable saddle point of your system, dynamical system. So this kind of superradiant instability is shown by these two gentlemen, Victor Cardoso and Oscar Diaz, to happen when the angular velocity of the horizon, measured from infinity, is larger than a critical value. So larger than a critical value set by the inverse radius of this ADS spacetime, which are often said to be 1, because this is as a reference. So if omega is larger than 1, these people 21 years ago had shown that the simple curve black holes in ADS4 is super radiantly unstable. If you encounter this kind of situation, an important question, which has been long-standing for more than 20 years, is what is the endpoint of the solution after these tachyonic modes condense and form a hair, non-trivial hair outside the event horizon? Roughly, this is the kind of question I'd like to address today. I'm using slides for lecture, but I prepared really little, slightly more than 10 pages. So hopefully you can interrupt me at various times. Yeah, I'll try not to rush. So far I explained to you some dynamical questions, but it will turn out to be more insightful to have a complementary thermodynamic viewpoint in mind, because these object black holes from mid-60s or 70s in the past century has been shown to exhibit a thermodynamic behavior. Okay? And the thermodynamic behavior that you have to remember to better understand the phenomenon that I'm going to explain today are the first law and the second law and the statistical interpretation of the solution black hole. First law simply says that the change of the black hole mass or the energy consists of two parts. The first part consists of the work that the outside system does on the black hole. And it also has a term which can be interpreted as heat absorbed by the black hole, which is characterized by the change of the area of the event horizon, interpreted as the entropy carried by the black hole. Okay. So first law is that the energy change and the work is related to the change of the entropy or the area of the black hole. The second law says that the horizon area or this entropy can increase or stay still but never decreases. Okay? So like the thermodynamic second law. One thing we should really remember out of this whole phenomena is that black hole carries entropy, which should be viewed as log of the number of quantum states at given value of charges. So throughout this talk, we'll be regarding a black hole solution as representing an ensemble of states at fixed charges, like energy, angular momentum, and charge. With this kind of understanding in mind, the dynamical instability that I explained to you in the previous slide can also be understood in the thermodynamic fashion as follows. I explained to you that dynamically, Cardoso and Diaz have shown that when the angular velocity of the horizon is greater than critical value, it's dynamically unstable. We can also see by black hole thermodynamics that it's also thermodynamically unstable, meaning that it wants to evolve in a way that it emits a particular kind of matter and increase entropy. Let's see that. In order to explain that, I have to quote a simple fact about the energies and angular momentum carried by all kinds of matters in ADS, matters or black hole, whatever phenomenon in ADS. It's satisfying this kind of bound. Whenever matter is going to carry angular momentum, it should also carry energy. And the energy carried by the matter is bounded from below by angular momentum, roughly looking like this. From the CFT dual perspective, we call it the unitarity bound of a CFT. Precisely, its energy no lesser than J plus some order one number. But in this talk, since I'll be mostly interested in configuration carrying macroscopic energies, roughly the bound is given like this. Okay? And it's approximately saturated by some states of matter, which I'll explain to you further in this talk. The point I'd like to emphasize is that if a black hole has an over-rotating event horizon, it can increase its entropy by emitting these kinds of hairs as matters as hairs, saturating this unitarity bound. And it can be easily seen by studying this black hole first law. It's the change of the entropy is given by for instance, I'm now considering configuration which doesn't carry any electric charge. But the change of the entropy is related to change of energy minus change of the angular momentum. Okay? So this delta E and delta J are the change of the black hole energy and angular momentum. And since I'm suggesting the black hole to extract a matter mode saturating E equal to J, both delta E and delta J are the same. and negative because black holes are losing energy and angular momentum. So both delta E and delta J are the same. You get an entropy change given by delta J times 1 minus omega. Delta J is negative. If the black hole is overspinning, omega is also greater than 1. So the entropy change is positive. Meaning that if black hole can somehow emit this kind of matter, it can increase entropy rather than decrease it. So this kind of process is not just dynamically preferred, it's also thermodynamically preferred. We'll have this dual two alternative viewpoints in mind to develop a final solution of this endpoint question. And all that is remaining to be done in the first half of this talk is to see how this kind of pair emission mechanism is concretely realized. So the interest of the general relativity community for the past 20 years is to find time evolution of this unstable configuration. So if it has some super-relatively unstable modes, follow its time evolution and see what the endpoint configuration will be. This is a very difficult question. It's solving nonlinear Einstein's equation in a time-dependent manner. People only managed to do it numerically and so on. So it used to be a very difficult question for more than 20 years. Today, I'll present a closely related but slightly different solution. Present a solution to a slightly different problem. I'll present a solution not to the classical GR equation, but I'll present a solution to the thermal problem. You may not even notice what the difference of the two will be, but in the next few slides, it will be totally clear that I'm giving a solution to a thermal problem only, not a general relativity Einstein equation. Okay. It will be a thermal configuration that I suggest, free of instabilities, but have bigger entropy than the original unstable co-ADS black holes. Okay. This is what I'm trying to do. Any questions? So with this kind of background in mind, let me first explain to you the situation with co-ADS4 black holes. Okay. Similar structures apply to higher dimensional ADS black holes, but as a prototype, I'm going to explain ADS4. I'm going to explain what kind of co-ADS black hole exists, when they are stable, when they are unstable, and when they don't exist. And the best way I think to do that is to show the situation on the charge diagram. The horizontal axis is the angular momentum rescaled by multiplying Newton constant, and the vertical axis is the energy, again rescaled. So if black holes carry macroscopic charges, energy and J are inversely proportional to Newton constant. I multiply Newton constant to them and in this case, yeah.
Sorry, what is a ADS black hole?
ADS black hole. So it's a black hole in asymptotically ADS spacetime. ADS spacetime is a spacetime with negative cosmological constant, maximally symmetric negative cosmological constant, like the one we have seen on the board in the previous slide. We want to consider some excitations on this ADS spacetime, where the black hole is at the center. Black hole is at the center of the ADS. Okay, so it's a black hole having event horizon at the central region of ADS. But if you move far and far away from this core region of black hole, it asymptotes to some ADS metric that of similar sort that we have heard.
How different is it to the cylinder you showed?
How what?
How different is it to the cylinder you showed earlier with the super radiance?
Cylinder. Okay. So to explain.
So you said the outer cylinder is ADS, right?
Okay. So this cylinder is a cartoon of ADS. So vertical axis is the flow of time. Horizontal plane is the spatial slice of ADS, whatever your dimension of ADS is. And if you go to the infinity in this radial, you always have a radial direction. I have a slightly different slice of ADS. It's called the global ADS spacetime. And the conformal boundary, unlike what Lorenzo explained to us in the first talk, will be taken to be temporal line times a sphere. So here in ADS4, the conformal boundary is S2 at the boundary times R. Is that clear? Or do you want to understand?
That's okay, thank you.
Okay. So this is a cartoon for ADS4. And in the central region, it's not ADS and it's a deformation. It's more complicated black hole-like configuration. Right. Let me explain to you what kind of situation that we see on the solution space of unhairy co-ADS black hole. The solution known for a long, long while, 70s or something, Carter or some people, if I remember correctly. So I want to explain to you the situation of these various co-ADS black holes by showing different regions on this charge space. I want to explain to you a few regions divided by these three colored lines. Okay? First line I'd like to emphasize is this red line. It's a line where the black hole solutions have angular velocity exactly 1, on the verge of being unstable. Above this line, the black hole has omega smaller than 1. We're all in this red region. Any point of this in this red region holds a co-ADS black hole, which is super radiantly stable. If you move down from this red line, you move to the region, blue region, where omega is larger than 1. So all the solutions here on this blue strip is the super radiantly unstable one that I explained to you in the cartoon previous slide. We like to understand the endpoint of after the condensation of all the unstable modes of black holes in this blue region. Another region I'd like to emphasize is this white region, because the blue line is the boundary of where the black hole solutions exist. Technically, we call it extremal black hole at 0 Hawking temperature. Below this energy for given angular momentum, no unhairy black hole solutions are known. This is slightly odd because I explained to you that in ADS spacetime, black holes or any matters carrying angular momentum should carry energy larger than that as a kinematic bound. So nothing can exist. No physical states or black holes representing ensemble of states can exist below this bound. It's just kinematically forbidden. That's good because there's no solution there. But above this kinematically bound, in this white region, there could have been existing some black hole solutions because no kinematics of ADS or CFD forbids any macroscopic number of states from being there. But on the space of co-ADS black holes, we find nothing. So two questions I'd like to answer in this talk is about this blue and white region. This blue region, unstable solution of the perturbation, should flow to a hairy black hole configuration with larger entropies, which would be better representing the black hole thermodynamics and the gravitational thermodynamics at these value of charges. What are they? That's the first question. The second question I'd like to address is about this white region above the kinematic bound. The absence of black hole solution. Is this something fundamental or something accidental just on the space of this particular black hole solution space? I'd like to answer this second question as well. Point clear. So, what I'd like to do is the following. As I told you, I'm going to suggest to you not the solution of the general relativity's Einstein equation. I'm going to suggest, that's too difficult for me and my collaborators. I'm going to suggest to you the solution for the thermodynamics of this black hole configuration involving black hole. And the general expectation we have is that if the black hole, core black hole has omega larger than 1, it's unstable. It wants to emit some matters carrying E equal to J, we expect, and gradually reduce its omega until it becomes no longer unstable. Okay. It will gradually have its omega reducing by emitting some matters until its omega becomes almost 1. Okay. Strictly speaking, slightly smaller than 1, so it's no longer unstable. So we're going to find this kind of endpoint-like configuration. We're going to study the black holes and the emitted particles, especially their thermodynamics, on the verge of being unstable. Omega very close to 1, but slightly smaller. That's what we're going to find, and that's where we're going to find a configuration which we suggest to be the endpoint configuration. Let's do it in one by one. We should consider the black hole at the core, where omega is 1, almost 1, and we should be discussing lots of amounts of hairs emitted out of this black hole because it wants to be stabilized. But in foresight, let us first study the thermodynamics of the emitted particles, gas in empty ADS first, not with the black hole with omega equal to 1 at the core. Okay? In foresight, this will be very useful for the reason you will see. So in order to make the discussion, I should have done everything in the gravitational language, but somehow my way of phrasing is that I generally tend to use the conformal field, quantum field theory language holographically due to this gravity at the boundary, but you can translate everything that I said into a purely gravitational language. So I'll be addressing this thermodynamics of these emitted gas particles in MPADS using sometimes conformal field theory language, but many of the formulas just will go through, even if you address it in gravitational words. So I'll be considering the thermodynamics of these emitted particles at finite temperature and finite angular velocity, just as a temporary tool to better understand microcanonical dynamics. And if you want to study that, you can study this partition function. It's traced over this Hilbert space of this gas, and it's weighted by fugacity, beta conjugate to energy, and omega conjugate to angular momentum. And when omega is very close to 1, you can really convince yourself that this trace over the Hilbert space of this emitted gas diverges because of the following reason. So in quantum field theory, conformal field theory, the states in ADS can be represented as local operators in 2+1 dimensional conformal field theory. For instance, you can start by considering some conformal primaries, and you can form the conformal descendants by dressing it by these derivatives. Okay? That's the structure of the local operators in conformal field theory. And you're going to consider a sequence of infinite sequence of operators which asymptotically saturate this bound that I explained to you. And the operator takes the following form. You have a core operator, primary operator, and you dress it by arbitrary number of a particular combination of derivatives which carries j equal to 1 and e, the scale dimension, equal to 1. So they saturate the bound, derivative part. If you move on to the modes which carries very large angular momentum L, those modes are causing divergences because the fugacity factor carried by one derivative has e equal to 1, j equal to 1. So a fugacity factor inserted for derivative insertion is e to the minus beta 1 minus omega, which is almost 1 if omega is close to 1. You have an infinite sequence of operators, and asymptotically, they are weighted by the same fugacity, not suppressed. So the trace will be almost diverging due to this sequence of conformal descendants, asymptotically saturating this bound. Okay? You can really do the computation by computing the partition functions of these operators. For instance, assume a particular conformal primary, and you make the sum for the ideal gases of these Bose-Fermi gases. For instance, if you like, when omega is close to 1, you can really see that this free energy for this partition function diverges due to the fact that the fugacity factor for derivative becomes almost 1, unsuppressed traces. The divergence you can show is inversely proportional to 1 minus omega. For detail, you have to do some computation, but it's easy to get convinced that there should be a divergence, right? Because the fugacity factor no longer suppresses this infinite tower. Okay. If you carefully look at the summation of these modes, those modes which cause this leading divergent part comes from the modes with very large angular momentum, large number of derivatives. You can really see that the divergence of this form is acquiring contribution from the modes which carries angular momentum inversely proportional to this 1 minus omega, because that's the point where it starts to appear the damping factors. This factor becomes substantially smaller than 1. If you transform all these observations into the ADS gravitational language, you obtain the following observation about the wave functions of this large angular momentum modes, causing the leading divergence of the partition function at omega close to 1. This is the following. The observation is that if the wave function, you consider wave function in antidistant spacetime with large angular momentum along it, okay, its wave function is peaked at a very large radial distance, far away from the central region of ADS. That can be easily guessed by considering that the stabilized position of the wave function, if you like the probe particle, is obtained by balancing the gravitational attraction of the ADS box, because it's a box, which is universal, and the centrifugal barrier that's formed by angular momentum. L becomes larger and larger, centrifugal barrier will be larger and larger, so that the stabilized position of the wave function will be very, very large, proportional to some power of the angular momentum carried by the mode. Okay? So the wave function of the modes dominantly contributing to this leading part of the free energy gets parametrically far away from the central region of the ADS, where the black hole at omega equal to 1 is supposed to sit. So the black hole, when it deviates substantially from vacuum ADS is dominantly located at R equal to order 1, the size of the box. The gas has very large angular momentum at omega close to 1, have their wave functions parametrically far away separated from the core region, which give us a possibility to approximately superpose the two configuration and propose a thermal configuration which is free of instabilities. Generally, the hairs and the black holes will non-trivially interact, form very complicated configuration, but at omega very close to 1, the fact that the stabilized wave function of the matters is parametrically far away from it, the core of ADS, it allows you an approximate superposition principle about the two components, the black hole and the hair part. So this leads the following.
Yes,
please.
Is there some CFD interpretation also? That's a
great question. I don't think I really understand well, because the configuration that I'm going to suggest is having black hole and the gas. Well, if you know some ADS CFT facts a little bit, these gases emitted are corresponding to some confining degrees of freedom, like mesons and so on, trace of some operator. Black holes are more really representing some deconfined degrees of freedom. The picture I'm going to suggest is suggesting that this confining and deconfining degrees of freedom are somehow superposable with two components coexisting. For field theory, I don't know how it should really be happening. I don't think anybody understands it well. Yeah.
And if you think about the radial direction as an energy scale, that's...
Yeah, probably that should be the case, but the thing is that the energy carried by the black hole itself, the mass of the black hole, and the modes which are very far away will be carrying similar energy. So you should be making a more elaborate thinking about the energy scale separation of the two components, but presumably that's possible, but I don't think anybody has got a very concrete understanding. It's quite interesting phenomena that I think we're lacking detailed CFT understanding. It will be a curious suggestion that our gravitational studies are making. Anyway, the suggestion, it's a very bold one. I know that I gave this talk many times to different audiences. Those people who love GR really hate this part, but I don't know, because I'm not doing GR anyway. They always care about the back reaction, the smoothness of the horizon. Well, anyway, so at least we can show that the leading back reaction of one component to each other is parametrically suppressed by the inverse power of the distance of these two components. But anyway, what we're going to suggest as a thermal configuration, free of instability, is consisting of two weakly interacting components in thermal equilibrium with each other. One, the core black hole at omega is very close to 1, and another, a thermal ensemble of gas at same temperature and same omega, very close to 1, in equilibrium to each other, because we are interested in equilibrium thermodynamic configurations. Okay? So we, meaning my collaborator Minuala, named it gray galaxy type, hairy black hole configuration. Galaxy because the hairs are rotating, it makes them flattened. Galaxy-like configuration. Gray because there's something black in the center. Okay. Anyway, since we are assuming this weakly interacting superposition of the components, you can compute the thermodynamic quantities, energies, angular momentum, entropy of each component and add them to get an information about the thermodynamics of the full configuration. Okay. Now we're converting ourselves to a microcanonical setup. We compute the gas contribution of these all extensive quantities, energy, angular momentum, and entropy, from this asymptotic diverging free energy contribution. You can take derivatives with beta and omega suitably to get a contribution of the Hare contribution of E and Hare contribution of J. With this expression, they turned out to be approximately the same when omega is very close to 1. This is a parameter which diverges when omega goes to 1. Okay, so the omega is very close to 1, but its slight separation away from 1 is giving rise to a free parameter, which can give rise to macroscopic charges that the hair can carry. And we tune this small omega, 1 minus omega, to be such that the hairy configuration carries the charges comparable to the one black hole carries. So we tune it to be 1 over G. Okay? So it's the same order of charges carried between the same order of charges are carried by hairs and the black hole. This is a free parameter, another free parameter of a hairy black hole solution. Okay? So in order for the hairy black hole to carry substantial amount of charges by the hair, we take this small 1 minus omega to be scaling like a small G Newton, semi-classical G Newton in a particular manner. With this scaling assumed, you compute the entropy contribution from the hair, you get something like this. And the C is a coefficient which depends on your conformal primary spectra, depending on beta only. You compute the contribution of entropy carried by the air, real thermodynamic statistical entropy. You get a scaling 1 over square root of G, which is much smaller than the Beckington-Hawking entropy carried by the core black hole, which scales as 1 over G. The upshot is that if you consider this system, charges are distributed between the core black hole and the hair part, and all being at the same order. But the entropy of this configuration is dominantly given by the area of the core black hole. So with this picture understood, let us consider the situation of this new configuration, again on the same charge space, angular momentum and energy. To understand this configuration, you start from a core black hole carrying omega almost equal to 1. So you start from 1 point on this red line. It represents a particular core black hole. And to realize this additional amount of charges carried by the hair, you move up 45 degrees in this charge space. You rescale it properly, it becomes 45 degrees. Starting from this red line, moving up by arbitrary amount you desire, because this is a free parameter, you can end up in any point in this red region, a blue region or white region. Okay? You can easily see that. Starting from any point on the red curve, move 45 degrees of freedom, you can sweep the entirety of this blue region or the white region above the unitary bound. So this provides a statistical thermal configuration. Thermal because we explicitly regard the gas as an ensemble of particles, so on, which completely accounts for the thermodynamics of the blue and white region. Okay? So in our proposal, what happens is that if a hairy black hole constructed this way stops at the blue region, it becomes a candidate for the endpoint thermal configuration of the unstable unhairy black hole carrying the same charges. You're suggesting that that would be the final endpoint configuration. If the hairy black hole stops in a white region, it will be a macroscopic entropy configuration containing black hole, where the unstable black hole failed to cover. But it covers all the way above the kinematic bound, right above the kinematic bound. So it provides the answer for both questions I proposed. In the blue region, the configuration I suggested could be the endpoint of the unstable black hole. In the white region, there are new black hole-like configurations. Okay.
This gas around can be also made of gravitons, or you're assuming that there is some matter?
There could be matter. The conformal primary part, I didn't really assume anything, but the results I explained to you, the divergent part, at least the omega dependence is universal. So it can be really gravitons, it can be spin zero matters. I mean, these are very universal structures. Yeah. Yeah. It depends on, the matter contents decides this overall function C as a function of beta, but the leading divergent part, 1 minus omega dependence, that's universal. And anyway, we are translating everything into a free parameter, so every structure that I told you is very robust, no matter what the matter is. Thank you for the question. Any other comments or questions? It's very.
So you're saying that there exists in principle new gravitational solutions that one should be able to find. I see you say numerical, but
Yes. The thing is that there are some very hard numerical calculations that have been done by Paul Chesler. You really start from perturbing unstable solution, evolving for some time numerically, but he couldn't do it for so long. So he did the best until he could evolve. But he didn't find any signature for its stabilized to a definite solution. It just keeps evolving. And that's actually our proposal for the GR solution, because, you know, the kind of hair that can be carried is so diverse, and actually they form a big ensemble. The natural proposal with our thermal picture configuration is that if you try to solve the GR equation, time-dependent one, it will never stabilize, but just keep evolving in the ensemble. That's our natural suggestion. Evolving in the ensemble of these hairs. You know, these hairs, and that seemed to be moderately consistent with the numerical simulation done by Chesler. So that's a very funny suggestion. You know, people have been seeking for endpoint configuration for 20 years. We are suggesting that this endpoint, definite endpoint, will not exist. Yes, so, but that's just a suggestion. Any other questions? Yeah, so this is roughly the story for core ADS black holes. We have, now you see the clear sense in which we are suggesting a thermal configuration. It's free of the instability issue because the core black hole is not unstable. And it has bigger entropy because I've explained to you in the earlier part, due to the first law, if the black hole, core black hole emits a hair saturating this bound, the entropy should increase. So it's always providing to you a configuration with bigger entropy than the original unstable black hole solutions. Okay. Okay. In the remaining time, I'll quickly go through the further developments. I try to be more qualitative. So far, I was also qualitative, but I'll be more sketchy. You can generalize in many ways. Most importantly, you can generalize it by turning on electric charges. You can have energy, angular momentum, electric charges, all of them. Or you can first consider the simpler configuration in which the black hole carries energy and electric charge only, not rotating. Actually, the black hole carrying energy and angular momentum, stability has been observed for these configurations only. You consider Rice-Nordstrom black holes in ADS. It really depends on the theory of your consideration, what kind of matter that you couple. But if you couple suitable matters to Einstein gravity, let's say charged matters and so on, it has been discovered a long time ago by Stephen Gopser and people that the black holes, particularly Gopser studied black brains, they can be kind of similarly superradiatively unstable in this internal direction. So black holes carrying charges with too large chemical potential for the electric charges can also be unstable for similar reasons. But since things depend too much on the detailed theory we have to consider, unlike these Kerr black holes where the results are quite universal, I'll be, for definiteness, consider the black holes in ADS 5 times S5. Partly because that's the favorite model by string theorists, partly because this is a setup which has been studied in detail by other people during the past 10 or 20 years. I'll be studying ADS 5 times S5 and charged black holes here. For simplicity, I'll turn on, S5 has lots of colors applying momentum. So it gives rise to lots of electric charges in ADS. So SO6 has 3 electric charges. For simplicity, I'll just take them to be equal for the discussion below. Okay? So with this precise setting, it turns out that if chemical potential for the electric charge is larger than a critical value, again with ADS radius equal to 1 unit or something, the black hole can emit matters saturating this E equal to Q bound. This is on another unitarity bound, and emit this matter and increase the entropy. Similar to the argument that I gave to the Kerr black holes. So again, from the black hole thermodynamics, entropy change by emitting certain matters carrying E and Q is given as follows. If you emit a matter saturating this bound, it's delta Q times 1 minus, which is smaller than 0. So negative times negative positive. So if black hole is overcharged in this sense, it can emit electrically charged matters and increase the entropy. And actually, the solution has been considered by many people. One of the first papers is another paper by Pollack, which I forgot to mention here. But there are many interesting works in the 2010 and early days. The thing is that if you naively consider the matter carry E equal to Q, let's say in N equal to 4 Young-Mills theory due to this ADS5 times S5, it's like this simple operator in N equal to 4 Young-Mills. We call it half BPS operator. Take trace of some complex scalars, and these are the Kaluza-Klein graviton particles. If you like to consider these wave functions, I mean these as hairs, you consider these wave functions in the black hole background. Unlike what happened for the curved black holes, it carried large angular momentum for the emitted hairs. These are S waves, not carrying angular momentum, just charges. So the wave functions, even if the charge carried by this is quite large, the wave function for typical Kaluza-Klein gravitons are centered around the central region of ADS because it has no centrifugal barriers. So unlike the argument that I gave for the modes, hair modes carrying large angular momentum, we cannot obviously getting a parametric separation for the wave function part and the core black hole part. So naively, no weakly interacting construction seems to be possible. So people in the early days turned on some hair modes for these Kaluza-Klein fields and worked out the Einstein equation very extensively with the back reaction of each other taken into account. So these led to lots of numerical solutions, which are very hard work. Very recently, we discovered that a very odd but novel weakly interacting picture is possible. For this, we have to borrow some facts known in string theory, which I'll just quote, which is known that if a large amount of charges carrying the charge of this Kaluza-Klein graviton is excited in a coherent manner, these Kaluza-Klein particles carrying large charge, collective excitations of these Kaluza-Klein particles carrying a large number of charges can be better described by extended brain-like objects in string theory rather than particles. We call these brains giant gravitons. Okay? So if they carry large charges, it's very well known in many senses that Kaluza-Klein particles description becomes not good. Instead, you describe it as an expanded object carrying a similar amount of charges. These are called giant gravitons. And the giant gravitons that I'm interested in this kind of configuration study is called the dual giant graviton. It's a D3 brain, which is point-like on S5, moving around, but it expands into a three-dimensional spatial object, which is basically wrapping the black hole. It's a spherical object occupying a definite radial location of the black hole I explained here. So it's a cylinder. Distance away from the center of the cylinder is finite and fixed. And if you emit a substantial amount of charges coherently, to be carried by a dual giant graviton, like n square order, 1/g Newton order, the radius location of this large expanded brain object is parametrically separated away from the central region of the core black hole. So you can again use the approximate superposition principle of the hair part and the core black hole part. That's possible only when you use this coherently excited brain-like configuration as a hair. So it's kind of exotic hair, right? You can again show that maximal entropy gain is obtained by emitting as few number of B brains as possible. So in favorable situation, you can just obtain one or just a few D brain objects. So they're carrying large charges. So their stabilized radial position is parametrically far away, and it allows you to do weakly coupled superposition principle, very similar to what I explained to you for the gray galaxy type configuration. For the charged unstable black holes, the hairs are exotic dual giant gravitons. That's what I'm suggesting. Okay. Anyway, I rushed through a little bit because I didn't want to repeat similar story again and again. The final thing I'd like to really do is to consider the generalized setup in which the black holes carry energy and both electric charge and angular momentum. Because first of all, this gives a more comprehensive viewpoint about the black holes and the spectrum of quantum gravity, carrying all possible charges. More importantly, if you construct these hairy black holes, you can provide a more quantitative test about our suggestion. We suggested many things which look nice in certain aspects, but I really want to make a quantitative test of this kind of suggested object using holography. So let me briefly go through. I have some time.
You have about 9 minutes.
Okay, I'll go through. I have 2 slides left. So again, we stick to the favorite ADS5 times S5 black hole. Here the charges are a lot. Black holes can carry a lot of charges. ADS5 has a spherical S3 section, so you can carry 2 angular momentum, J1 and J2. S5 can carry 3 angular momentum, but for simplicity of presentation, let me just take the situation where 2 angular momentum are equal, 3 electric charges are same. So the black hole carries E, Q, and J. Let me explain the situation of this solution in this 3-dimensional parameter space. So charge, angular momentum, and energy, just like I draw J and E diagram for co-ADS black hole. 3-dimensional plot is complicated, so I'm going to make a slice. I fix the J, and I show you the 2-dimensional slice of Q versus energy. Structures are quite similar to what I've shown in curved black hole. There's first of all unitarity bound. And we all know that it's a superstring theory. So this unitarity bound is often called DPS bound, a bound which saturates supersymmetry. So this blue line is the unitarity bound. Nothing can exist below. Many things can exist above. The solution of space of unhairy charge rotating black holes in ADS exists above this orange line. Again, this is the 0 temperature limit extremal black hole. It consists the BPS unitarity bound only in a codimension 1 subspace. Generically, it's on top of it, like the extremal curved black holes versus the unitarity bound in the previous slide. Anyway, above this extremal black hole line, some black holes can carry mu larger than 1, electrically unstable, omega larger than 1, angular momentum unstable, but curiously not both. Either one of these two are larger than 1 or none are larger than 1, but never both larger than 1. I don't have a deep understanding, but that happens with data. So mu equal to 1 curve is here. The region below this mu equal to 1 is mu larger than 1. So black holes in this region wants to emit electric charges in the form of the large dual giant reactor. So it forms the hairy black hole of the second kind. I explained to you this too. This region, the black line, is omega equal to 1. Region below omega equal to 1 is omega larger than 1. So it wants to emit the hair as a gray galaxy. So one of the two hairy black hole mechanism happens to account for this gray region, but we don't have to use both. Two regions are pinched and divided by a BPS extremal black hole, which is represented by this point. And this white region above, things are all stable. So depending on which region you are at, you can use either gray galaxy or dual giant black hole, dual giant black hole configuration to account for, to construct a more dominant, stable configuration. The full 5 or 6 parameter generalization has been studied in our paper. An interesting part is that just like a curved black hole, where we either construct the hairy black hole representing an unstable black hole, or found a hairy black hole where no unhairy black hole solutions are known, we find either type of hairy black holes in the white region between the unitarity bound and the extremal black hole line. The hairy black hole configuration exists all the way bound to unitarity bound, also in this case. Okay? It's similar to what I explained to you for co-ADS black holes, finding everything all the way down to the unitarity bound. Now it becomes slightly more interesting in some sense, because the limiting hairy black holes that we constructed on both sides are supposed to be supersymmetric hairy black holes, or supersymmetric hairy hairy configurations. This type of limit can be tested by using the power of this funny supersymmetry. Okay? So it can be tested in the following way. So if you have hairy or unhairy black hole, you can compute the entropy of this black hole by computing the area at given charges and make a gravity prediction, the black hole prediction, for what the entropy or the Hilbert space dimension of the theory should be at that value of charges, right? But using now holography, using the fact that ADS5 times S5 is holographically dual to a boundary n equal to 4 Yang-Mills superconformal field theory, you can make an alternative independent counting of the dimension of the supersymmetric Hilbert space and compare with the prediction of the black holes, including our hairy configurations. Okay? That will be a quite quantitative test of the gravitational picture that we are suggesting. And we have done that in our recent paper earlier last year. So a technical way of easing this kind of field theory calculation of entropy is to study what's called the Witten index. It's a partition function which counts bosons and fermions with opposite signs. So the bosons and fermions can partly cancel. You can again weight it by the various chemical potentials, conjugate to the 5 charges that the DPS operator can carry. Okay. I'll shorten the discussion a bit. Anyway, we can calculate this index using field theory. And the offshot is the following thing. Okay? So the thing is that roughly we fix, so in order to do the calculation easily, just brutally using computer, we fix n to be as large as possible. N we thought is large. N squared is 100, so it's quite large. We also took some charges to be large, like order of n squared. What we happen is that we plot the entropy predicted by both from the index and the gravity area law as a function of one angular momentum while fixing some other charges. Okay? So the prediction and from field theory and gravity goes as follows. The blue line is the Beck-Einstein-Hawking law prediction by the unhairy black when it's more dominant. When certain angular momentum becomes larger, gravity predicts that a hairy black hole should have more dominant angular entropy, which is the orange line. The field theory calculation we did at n equal to 10, and the entropy normalized by n squared, is this red dot, which we think very closely follows the hairy black hole curve when it's supposed to be dominant. So we think it's a very interesting semi-quantitative test of the configuration we made. We did something similar for the dual giant gravity-contrast black holes. Unfortunately, to the numerics that we could do, the distinction between the unhairy black hole and hairy black hole, the gravity prediction is not very different, sonorantly different between the unhairy and hairy one. So we couldn't confidently test anything. We could neither test or falsify a suggestion. But for the gray galaxy type configuration, we could quite confidently test that our field theory is indeed seeing the entropy of the hairy black holes when charge is set to certain regime. Oh, okay, I'll briefly finish. I explained to you the 2 types of hairy black holes, and I explained to you some tests in the supersymmetric limit using the counting technique of these black hole microstates. In the next lecture, as advertised, I'll be explaining to you these microstate countings and construction studies in more detail and try to apply it to hairy black hole, getting an alternative your quantum field theory picture of the hairy black hole I explained to you today. Okay, so I'll finish here. Thank you very much.
So we have time for a couple of questions. There is a question online from Kobus Labaskachny. He asks, not sure if this is relevant, but could one conduct an astrophysical test for charged hairy black holes and hence get experimental evidence for ADS /ELT? Just curious.
Astrophysical implications of probably. So yeah. If you want to compare it to observable black holes, before getting to black holes, first you have to observe negative cosmological constant in this setup, which doesn't exist. So from the starting point, it's the wrong one. I'd rather say this is a good POI model for discussing quantum gravity spectrum, but the connection to observable black holes and so on, maybe there might be something in direct lesson, but I'm not really sure if there will be any direct.
About the index of the one, what's the argument for reading of the entropy from the index? But that's not a partition function.
Y index agrees with the entropy, which counts boson plus fermions. Yeah. There's no a priori fully first principle argument. You know, the pragmatic attitude from decades ago is that, you know, index is a lower bound for the true entropy. Counted at large charge macroscopic order, the cancellation is somehow not substantial, so they are at leading order they equal. So that's an observation. There are more elaborate arguments on why that should be the case, but It's not a really, I think, first principle field theory argument.
But here we assume that the index is the partition function, kind of when we just take the log, then we get it.
Yes, take absolute value and log. And the thing is, I mean, it's not a precise argument, but the rough feeling is the following. So, you know, at very large charge, I mean, there will be zillions of states contributing to E to the entropy. There are zillions of bosons and zillions of fermions, maybe 2 zillion, 1 zillion. Subtraction is another zillion. If you take log, the leading entropy is not really changed by the coefficient factor 2 or not, unless the cancellation is really fine-tuned. So that cancellation of zillion and zillion is giving rise to just million. Then the leading order entropy will substantially change. Okay, so probably I'm assuming that this fine-tuned cancellation is not happening, which is still an assumption, but I think it's not that unnatural.
Yes. Can you say again that in which case you get the dual giant gravity, and in which case you get the gray galaxies?
Yeah. So the dual giant, like the charge theory black holes are obtained when the black hole is overcharged, so that its chemical potential is large. It wants to emit electric charge and become entropically more dominant. When omega is much larger than 1, if it's over-rotating, it wants to emit J.
Yeah.
Okay? So these are very different kinds of hairs it wants to emit. Somehow the two doesn't happen at the same time. So when it's overcharged, it's the dual giant hairy black hole. When it's overspinning, it's the gray galaxy type spinning hair black hole.
Sorry, but what happens if you have both conditions?
We don't know, but it just doesn't happen. You know, it consists the solution space of unstable charge rotating ADS black holes in all dimensions. Both doesn't happen at the same time. Maybe there might be a good explanation, but it just doesn't happen on the unstable and on the unhairy black hole solution space. You know, it's always one chemical potential being larger than 1, another smaller than 1. They always get pinched off by unhairy supersymmetric black holes and get split. There's no region where both of them are larger than 1. Somehow there might be a simple way to explain this. I'm not really sure. Yeah, it's the observation.
Right, so let's thanks one second.
Very much.
Then I was like, no, it's all. I was like, that's why we do those questions. That's just funny.
We see that. Well, how low is it?
That's what I'm saying. It's a little more like
5, 6, 7.
yeah, like and
I didn't realize. Just give me a second, just to.
Yeah, exactly.
And it just
That was pretty
when it could best ever.
and stuff.
More fluctuation at lower end. But when we quantitatively really so long, is that black also roughly following?
He couldn't keep contain himself.
Yes, and you can find it still in phase.
He couldn't contain himself. Like, I'm this is
Hello. Oh, yes, I see. Sorry. Maybe
don't get it.
just move a little bit.
That's so
And I'll put my laptop there. Yeah, please.
That rap.
Anything in approximating this resistance?
That's what I was saying.
I'll show you.
Okay.
Probably in that.
Yeah.
It's good to see the deviation from, let's say, N equal to catiform. Catiform is in a way like blackboard.
Diagonal plane. From the code. Yeah.
Standard reference.
From a diagonal plane, right? Like a off.
Truncation might be valid.
Yeah.
Otherwise, you have to sum of everything.
They say they're recorded.
Okay, let me show you.
Yeah, I didn't understand that. The point is that it. Yeah, nah.
And then this is my part. Because
Maybe blue is the better guide.
blue is the better color, okay?
Just that, yeah, more common.
I think it's fine. It's probably mine.
Okay. Hi. May I start?
Should be good. We can wait in front of you. So the next speaker is Palav Bhatt from Princeton University.
Hi. Thanks, Anush and Rob for inviting me. So, and I think this is the last talk. So what I'm going to talk about is some of my ongoing work on diagonalization of a large matrix, RMT transition, and some SYK-like models. And so I'll be talking about one of my paper. So this is archive 2509.04075 and some other ongoing works. Okay. So is that pane fine? Right. Okay. Oh. Okay. So what I'm going to talk about is that first, let me introduce a few things which most of the students may not know. What is this RMT random matrix theory transitions? Now, you can, if you take a very, it's almost not working, not visible.
You say it's a little bit too small. If you can just write a little bit bigger. You can try the black. I know it worked.
Okay.
The black
There is no ink, it seems like.
Let me
Yeah.
ask.
Yeah. Okay. So if you take a big matrix and with many entries, say n cross n square entries, of course, and you diagonalize that matrix, this is, you are reducing from n square to n variable. This often has similarities with what physicists call renormalization, that you start with many parameters, but you get an effective theory with less parameters, roughly speaking. It's not an exact correspondence for various reasons, but of course, this is a type of diagonalization is type of reduction of original number of variables to a small set of variables. And often, in certain cases, if you look at some collective properties of this reduced number of variables, they show various features suitably defined like universality, etc., and many other things which we'll discuss. So what I'm really talking about, one good example of such a scenario is what is known as, say, GOE or GUE. There is also something called GAC, which I'm not getting into immediately, matrix models.
Definitely no markers are gonna.
Oh, that's fine. That's fine. Okay. Okay. So what happens for these models? What is a GOE matrix model? GOE matrix models is a simple model where you have these entries Mij and Mji, and they're real. So I'm describing the GOE matrix model where Mij is equal to Mji, and they are both sampled simply from a normal 0-1 distribution. Normal 0-1 means Gaussian distribution is 0 mean and 1 variance. Such a model is called GOE matrix model. Okay, now if you diagonalize them, of course, we know the story that you get Widener semicircle distribution and those kind of things, but this is not the most interesting universal property. What happens is that if you plot the eigenvalues from E zeros or lambda zeros to lambda n and look at these quantities like delta n, which is lambda n minus lambda n minus 1, that is gap of these eigenvalues, then this is a famous result that kind of satisfies this kind of distribution, very characteristics of quantum chaotic system. And what I'm plotting the density of these variables, and where I have taken delta and density of this new variable x is equal to delta n by delta n average. And that quantity, I am plotting the density of that quantity. And if you plot, you get this kind of behavior with what is known as level repulsion, that at near x is equal to 0, there is a depression and it starts from 0 basically, and it follows this pattern of e to the power minus, or this variable is often named s rather than x, so let me call s. So s e to the power minus s square kind of distribution, rho s, satisfies this kind of distribution. So this distribution in certain ways is universal. In one way it is universal is that if you add certain corrections, even non-Gaussian corrections to this matrix model, which has finite variance, etc., if you take a sufficiently large matrix model, you will end up getting this kind of behavior. You can also put some of the elements to 0, you will again get similar type of behavior. You can do various things. And in certain situation, you may not start with Gaussian orthogonal ensemble at all, but start with some physical system. And physical systems have Hamiltonians which are very sparse and not even random in any meaningful sense. So you take a quantum chaotic system like a quantum, just a pendulum, a double pendulum, something, and then after you take diagonalize a matrix of big matrix, etc., you'll again end up getting similar kind of distribution. So many different ensemble with certain symmetries, etc., will give you this kind of distribution. And that is not the only universal properties. We'll discuss few other universal properties, but all are coming from this difference of eigenvalues, sometimes their ratio, etc. We'll discuss another thing which is more interesting, which is called R ratio. But we'll come to that. That also shows certain universal behavior. We'll define it soon. So, what are the universality classes here? Means it is not true that all metrics will show exactly the GOE distribution. There is another, of course, another very simple, this is the GOE universality class. And So this is GOE that we have discussed, Gaussian orthogonal ensemble Mij is equal to Mji. The second class is called GUE, Gaussian unitary ensemble or class, where Mij is just Mij star, like just a normal Hermitian matrix, doesn't have to be real. And in that case, you can say that Mij and there is just an imaginary part. Okay, where it is obviously plus, it is minus, and again, all of these things, MR and MI, both here are satisfying again the normal 0-1 distribution. Sometimes it is scaled by √2, etc., but those things makes minor differences in the variance, etc. So this is another universality class. And if you do that, if you do the same thing for GUE rather than GOE, you get a little different distribution, which has a square e to the power minus a square behavior. So we go from e to the power minus a square to a square e to the power minus a square behavior for these densities, and also other inverse things, R ratio, etc., would show similar behavior, which we'll discuss. So this is why I'm calling that. So this is very much like deforming a theory. The second analog is that we do not only have universality, we also have relevant operator and those kind of concept. So the relevant operator means that, so if you start, can I erase a little bit? If you start with a GOE matrix, which is Mij is Mji, and add a very little perturbation of epsilon into some Aij, I epsilon into Aij minus I epsilon into Aij. So this is our Hamiltonian. So Hamiltonian perturbed is equal to a Hamiltonian GOE plus epsa into a very small G, means that epsa is the small parameter here, GUE Hamiltonian, and for normalization, we are kind of dividing everything by 1 plus epsa square. So what will be the eigenvalue distribution of this perturbative Hamiltonian? So if you look at these quantities, and of course is cousin R ratio, which I will discuss. So what happens for these quantities is that they will show immediately grow from GUE, because GOE is the first university class, and you perturb by a relevant operator, you are going to the GUE class, the next one. So once you turn on even a little bit of GUE, everything will be GUE. So you take a big real orthogonal matrix, real matrix, and add a very little complex deformation. If n is sufficiently large, you will get a GUE, a square e to the power minus a square, GUE-like distribution at the end. So this is the universality here. There is also something called GSE, I'm not getting into that. And Dyson has an old famous paper where he claimed that there is threefold way of quantum chaos. He said that only there are 3 types of Hamiltonian which quantum chaotic system can show. And it is basically related to what kind of symmetries they have, which I'm not getting into. Often in spin system, GOE happens if it is basically doesn't have a time. GOE happens if it doesn't have a time reversal symmetry. GOE happens when there is an anti-unitary time reversal symmetry, and GSE happens when the time reversal anti-unitary time reversal symmetry square is -1 in certain situation. So basically, from the time reversal symmetry in spin system defines whether the Hamiltonian will be GUE or GOE or GV. But even a small breaking of those symmetry takes you to the next universality class, which is not very surprising. Now, let me define for you now, go back to the discussion and let us discuss what R ratio is. R ratio is simply defined, if you define this kind of quantity like Rn, which is minimum of this new variable Sn, which is the difference of eigenvalues, etc., minus and Sn minus 1, you take two consecutive difference, look at their minimum, and divide by their maximum. So defined as such, this turns out to be calculable quantity. Like people can find out that what is the probability distribution not of S but of R ratio. And you can analytically calculate what will be the average R ratio for GUE and what is average R ratio for GOE. So if you calculate, you get a value which I'm guessing close to 0.51 or something. Here you get close to 0.59 or 0.6. But all these values you can actually analytically calculate at large N. And this R ratios too will show this behavior. So you have this Hamiltonian GOE. Immediately when you turn on IPSA, the perturbative R perturbative of this Hamiltonian will be same as R of GUE. But the story doesn't end here. Why these R ratios are even more interesting is that if you just take a 3x3 matrix, then you can actually find R 3x3 for both GUE and GOE for this complex matrix analytically. This perturbative thing you can calculate analytically. 3x3. And we will show that these kind of things could be used for some other thing. We will get into that immediately, but these ratios importantly could be calculated analytically for small matrices. Now, what happens? Now, whenever there is a RG involved, there is a scaling involved. So when GOE goes to GUE, it would not happen, means that it only happen if you take n larger, larger, and larger. It would not happen for a small n. Basically, for a small n, if you say n is equal to 100, of course, and make IPSA smaller and smaller, so 0.00001, and look at this spectrum, no way this matrix could have a R ratio spectrum, which will be more like GOE, not GUE. So all these things for finite n will be a smooth transition, not that it will happen for infinitely small IPSA. So when you take both n to infinity, n is like a cutoff of RG, and IPSA to 0, you, for a finite n, all the time, if you calculate these R ratios of this perturbative matrix with IPSA, you will see a continuous transition from its GOE value, that is 0.51 to 0.66 or something, which is RGUE. So another value. So you see a continuous transition for finite n. Of course, if you make this n larger and larger, this transition will become sharper and sharper. This is say n is equal to 10, this is n is equal to 100, and this is n is equal to 1000. It will become very, very sharp, and progressively it will happen for smaller and smaller epsilon. So just like in RG, if you have a cutoff and taking a relevant parameter to 0, you may ask that what is the scaling limit? Means that there should be some scaling limit. If IPSA goes as some power of n, then at the end, all these graphs which I'm drawing as the parameter of ipsa into n to the power minus alpha. So ipsa going to n to the power minus alpha means that ipsa into n to the power minus alpha is a new quantity lambda, which is ipsa into n to the power minus alpha, is finite. And if you plot these things with lambda, then all of these graphs will basically fall on one another. N is equal to 10, 100, and 1000, 10 to the power 4, everything will fall together and you'll get a smooth transition from GUE to GUE. In statistical mechanics, this kind of transition is called Pandey-Mehta transition, often called RMT transition. So, and this ratio is 1/2 for dense matrices. For dense GOE matrices, these ratios are n to the power 1/2. Well, means that this is plus, I think. This goes as n to the power minus half. So ipsa into n to the power half is lambda, which gives you a intermediate scaling limit. More interestingly, I was saying that R3 cross 3, you can calculate analytically. That plays an important role because it turns out numerically that R in cross n as a function of lambda is very close to R cross 3 with the corresponding value of lambda, but you put it in R3 cross 3. The scaling function you get at the end for large N is almost identical to the analytic thing you get at 3 cross 3 matrices. Sorry.
So this H perturbative for any finite epsilon is always belongs to GUE, right?
Which one?
H perturbative that you have written, which is H GUE plus epsilon H GUE. That whole matrix is
Ipsa is finite. And what is the value of N?
Well, I mean, for any N, it's only like for the quantities like R or, nearest neighbor spacings, you can compute them at large N. But for any small epsilon, any positive epsilon, the whole matrix is GUE.
It means for a positive epsilon and positive N, whole matrix is neither GUE nor GOE.
It's GUE, right? Because
it means nothing, means that it is a mixed ensemble for
the matrix is invariant under unitary symmetry.
Yes, but that is not the definition of GUE. GUE means that you fill up with random matrices where the real and imaginary part have the same variance. That's the definition of the GUE ensemble. Now,
I see.
Okay, so here that's not the case. So it won't be anything. But the claim is that at large N, it will actually become GOE. And this difference in variance would not play an important role. Okay. And this scaling limit is called Pandey-Mehta RMT transition or RMT transition. Good. Now, the thing is that these kind of transitions, you can ask various questions that what are the field theories, etc., which governs these kind of critical in this double scaling limit. There's a lot of discussion on that. I don't understand this literature very well yet, but we will do something very simple. So what people have done for this kind of transition is that it is very conjectural yet that this kind of scaling limit exists for all kind of GUE to GOE transitions. People looked at lattices, means that then you are not looking at any kind of Gaussian ensemble. Lattices are like lattice models or models of spin. Like, for example, this is a simple model is SIX is interacting with SIX plus 1. And you can also turn on the Y components. Sorry, last one is here. And then what happens is that you turn on some kind of SI, Z, and then there are models where you go from, again, GOE to GUE depending on whether you have this SZ component or not, and you can study this kind of transition. This is deterministic coefficient, J and H. They are not random numbers, but we know that for large N, this becomes UE, and if it has H or some other things, it becomes GUE. So is there a scaling limit here? It turns out that there apparently is a scaling limit. And some people claim that this coefficient, which was lambda n to the power minus alpha apparently is 1/4, not 1/2. Again, maybe not true even, because it's hard to do simulation accurately for very large N with a lot of spins like that. So we decided that as we are high energy physicists, we're not that interested in lattice models, which is very condensed matter, and we are interested in SYK models. Okay, so an SYK model, as you know, that a lot of fermions there, in fermions psi I, and then Hamiltonian is something like H is IJKL, and these fermions are interacting is K psi L, and J's goes as normal 0, 1. So in certain ways, they are very big cousins of GUE and GOE. And as it is a fermionic space, there's a lot of degrees of freedom. I think it is 2 to the power matrix size, which we are calling N before, but now I'm calling it L. Is actually number of fermion is better put the number of fermion L, the matrix size is N. It is if the number of fermion is L, then N is 2 to the power L/2. So the matrix is very big and sparse. So one can ask whether you have something similar to this kind of RMT transition for these kind of models. We'll look into it, but we are still not looking into this kind of SYK model either. We are looking at SYK-like models to begin with, which is more controllable. I think that Javeki has a paper on that. Your model is 5 minutes. I'll just finish it. It's a similar model where we replace the fermions by spin system. It is SYJKL, but A, B, C, D, now they are not fermions, but they are spins. But J's still goes normal 0, 1. These models have a lot of control over it. In a way that they're a little bit easier to simulate because there is no fermion, but it's a spin system. Now, what we did is that we also wrote a paper where we have found out that if we take this if we just confine ourselves to 2 coupling, like this kind of model, not 4 spin, but 2 spin, then also we get a quantum chaotic system. They may not be maximally chaotic and all those things. Those are investigation we're running. The thing is that then what we found out that, okay, if you have this kind of quantum chaotic system, can you study, for this simple at least, RMT transition in this kind of system? And for the SYK model, I should mention that there is a relatively recent paper, 2014 04963, which actually studied for a SYK-like model. They studied some kind of RMT transition, but they also didn't find out the scalings of those transitions.
The transition here is a function of what?
Sorry?
As a function of what? The transition happened here?
So I am getting into that. So what we have is
the people just ask if you can switch back to the black if possible.
Black, all these apparently inks are finished. I would love to do that, but you can see that you can't really do, now it's kind of working again. You have to rest. Okay.
I understand.
Okay. So the point is that now this model is general. Now, if we take certain version of this model, the GOE model roughly looks like Jij. You can construct SIX, SJX plus SIY, SJY. This is the GOE model, and you can have a corresponding, you can create many GOE and GOE model. But with two matrices, you can have SIX, SJY plus SJY interacting with SYX. So this is a GUI version of this model for odd n, I think, and this is the GUI version of this model. So as we have these things, we can look at this perturbative Hamiltonian, which is H GUE, again the same thing, from lambda epsilon by root over 1 plus epsilon square into H GUE, and look at this perturbation. But this is not the only version. We can go in the original work and have a GUE model which is with 4 spin, but GUE is 2 spin. We can reverse it. We can make GUE with 4 spin, GUE with 2 spin, and play with all kind of GUE perturbation and see what happens to these indices and similar kind of transitions here. What we are getting at least for two, the result seems that it is very similar to n is equal to half. We are not yet sure about the results with 4, 2, 2, 4, and other combinations.
These J's to be the same?
Sorry?
The J's are the same between GOE and...
J's are the same. J's are the same here. Same means they're all normal 0, 1. So they are not same.
Not the same.
No, they're not the same. They're just the random variables. This is one set of random variables, another set of random variables. Okay, good. So
SIs are polymatrices.
Sorry?
SIs are polymatrices.
Yeah, SIs are the polymatrices, local spin polymatrices. So basically, it is not, this is just one part. This is a tensor product of identities, etc. We're not getting into this. Okay, so this is what we are studying, and we are getting results which is similar to this with n is equal to half. We're looking at it. Now, there is another quantity I just quickly mentioned, like these authors discussed that. Another way to look at not R ratio, but you can look at these transitions by something more recent and fancy, known as Krylov complexity. So if you look at the Krylov complexity of a GOE matrix, then it peaks at certain point. Krylov complexity I'm not defining right now. So complexity you can define, you can take a random state, you can evolve with Hamiltonian, and you can define how it is diffusing in the phase space, and through that you can define complexity. And turns out that the peak of the Krylov complexity for GOE and GUE differs a little bit. GOE's peak goes from GUE's peak. So we can actually look at this change of this peak and look at, this is the peak value versus this lambda, and you can ask what scaling this peak value has. It turns out that again, we get n is equal to minus half like scaling for Krylov complexity peaks. So this is something also we are studying in the same work. And why this scaling happens, I think it is always n is equal to minus half. Those results, whoever did it was not very well done, because this actually is determined by, this is called Fermi-Golden rule. The idea is that this difference between, statistical difference between these things will become important when this delta of GOE will be same as the epsilon into not delta, but actual size of the eigenvalues of GOE. From that gives, this intuitive idea gives you n to the power minus half. This is called Fermi-Golden rule. But we are still studying and not sure that what happens if we do 4, 2, 2, 4. There may be some surprise there. So anyway, so
what is delta GUE?
Sorry?
Delta?
Delta, sorry, not delta, but SGUE. S means the eigenvalue spacing. Good. So I'll finish.
We have questions for a few minutes. Instead XY, why not XYZ?
You can have all these things. In original, you have 2, right?
Yes, yeah, but how does it compare with the SYK model?
In terms of maximal chaos, you think that's another thing we're trying to understand. We don't know, so what happened? Yeah. It may not be maximally chaotic.
Right, right.
So,
Okay. Any more questions? Okay, if not, let's thank Paolo again. So there is lunch now, and we return at 2 p.m. So it should be somewhere along that column.
Negative one.
Oh, sorry. Next.
Which is back.
Yeah.
Forward.
Some people that are small.
Conveniently placed pose.
I also kind of want to.
Horizontal pose. Nice.
Yeah, that's supposed to be.
It's the focus.
Okay.
Add like structure.
I probably will.
Let's
stop.
We can stop.
Yeah, just having.
Whether they like.
You're telling me.
No. So a few announcements. So if you are a vegetarian, please raise your hand. If you are a vegetarian, 1, 2, 3 vegetarians.
3, 4. Join.
So there are 4 vegetarians. So I apologize for not having a vegetarian option today for lunch. But from tomorrow onwards, there will be a vegetarian option. We not hire. So ask if there is a vegan. Vegan. Are you a vegan? Okay, so then I can ask any vegans. Okay. Okay, very good. So that was one. And the other one is we have meal vouchers for dinner. Every day we hand out meal vouchers. You can go to, there are some restaurants, you can go there and get food. So how many of you want meal vouchers for dinner tonight? Yeah, almost all of us.
Indeed, yes.
It's good to get a number, please.
Who doesn't want the meal voucher?
Yeah. Just one of you. Nobody.
One.
Okay. I got some pizza now. Okay, great. Wonderful. You really get all this one. So the food was not enough.
Ran out of budget there and asked people for the vouchers. Bro, yeah, he was. Oh, I forgot his name also, but he was funny, bro.
Okay, great. So I will make that. Yeah. Okay, great. So with that, we can start the afternoon session. Any other questions, comments? No. Okay, so our so we have 2 talks this afternoon, and they are 1 hour each, and in between we have a coffee break. So our first speaker is Professor Antalya Viskan from Brown University. So Antal will talk about emergent Hilbert space in collective creativity. Please.
Thanks a lot. Especially thanks for the organization of nice school. It started out very well. I hope it just goes up. I don't want to change the slope. Oh, it's great to hear all these talks. I'm sorry for this. This is a slightly different title from what I gave on what is written up. It's, if anything, it is more general. The fact is there will be 2 more talks on this subject, which will be probably more detailed. One by Hendrik van Zyl and another by Robert Koch. So he should be here. So I can take the luxury of being a little bit descriptive, knowing that there is some backup coming. So it is a problem of Hilbert spaces in general, in all these theories which are called emergent, meaning theories which come either from ADS, CFT, gauge gravity duality, those which are generated by matrix theories in general, Young-Mills theory. This problem is relevant to those. So let me start then just by, listing skips
If it fire breaks, then it's gonna skip. Just give it a second to just kick in.
Slide.
Last one slide. I can go without that slide. I hope it will not skip the other slides. So this the statement of that slide. Oh no, it's I forgot my own slide. It moved quickly up. It moved quickly up to talk about the phase transition, which typically happens in these emergent theories, and that phase transition has a very relevant parallel in black hole physics. The Hawking-Page transition. In QCD, it would be the confinement phase transition. And it's characteristic of these models. And it's one of the telling correspondences between gravitational and matrix physics. It only happens in the singlet sector of the theory. If you are studying non-singlets of the theory, even though there is a theorem of Mandelstam and Milken, the theorem said, the paper asks the question to gauge or not to gauge. And I say it doesn't matter, maybe, but I would still gauge if I do any calculations, relevance to black hole physics. Okay, and you will see why. So there are reasons for that. Let's see. Now, these multi-matrix models can be solved to some degree, especially lately by numerical methods. Okay.
Point it towards the laptop if you can while explaining. Maybe.
Yeah. Okay.
Towards the laptop.
Oh, really? Right. So there can be solved by numerical methods, which always Monte Carlo was always there, and there are nice results by Monte Carlo, and can never be taken too large in Monte Carlo, but there are bootstrap methods, which are very popular, variational, and then collective, which I will comment on much more. So these theories then are used to model emergent gravity, and for some time. It goes back to the success of the one matrix model in modeling two-dimensional gravity as the first example of D equal 1 to D equal 2 correspondence. So the states in this theory are graviton, multi-graviton. Then there are other exotic states like giant graviton. And lately we will hear much more about non-graviton states. So the map, okay, yeah. So the map from this matrix theories to some kind of gravity is achieved by single trace operators and then studying their dynamics or quantum properties. And we call those collective fields or variables. But they have to be a fairly general set, meaning all possible traces of all possible products. And it is a fairly large set based on which you are doing this map. Nevertheless, no, it doesn't move. Okay. So where do I go? This works?
Yeah, it works.
Okay. Came back. Okay, finally. So these are we call them long time ago collective variables. And if you have those collective variables, the traces in the case of a multi-matrix problem, and in that case, for example, you would have a matrix which is function of time. So such a collective variable would have the index of the matrix, the number of dimensions, 1, 2, 3 to D, but at each different time, and that we call a loop C. So the loop is a general word for a product of these matrices, and those are also called words. But that basically would be an over-complete set of these loop variables. But nevertheless, based on those variables, you can generate a closed equation. And I don't want to, even though those equations were publicized long ago for large or infinite n, I don't want to use that word for reasons you will say, because much of what we do is actually finite n. We never really do infinite n. But those collective variables obey this closed equation, but it is with a large infinite set of variables. And there is an action which I didn't write, and I can, if there is time, I can write it on the blackboard. So there is an action. There is also a Hamiltonian, which only involves those variables which are at equal time. So that's in accordance with canonical quantization, that you will be evolving from time equals 0 to some arbitrary time. So that cuts down in the number of variables because you will only have those traces at equal time. So I call this super completeness, and that's a property of these variables. And I will just feature the Hamiltonian, which has an explicit form, and this is derived long ago, and in a way. That box is a bit, needs a separate 10 minutes. It was defined by Migdal long ago, but it is such a derivative which puts into that C the Young-Mills equation of motion. So it's something to do with the Schwinger-Dyson equation, and it puts in what the box would be in Young-Mills theory, but the nonlinear equation of Young-Mills. But it is in that sense, no. Now, there are works going back long ago where Migdal tried to make some geometric, give some geometric meaning to that box. That was never successful, meaning even though this would look like interaction of strings, but to make that box a Laplacian of the string field theory, that's not so, even though you would like to have some geometric meaning, but it was not coming. But this Hamiltonian with these variables, obviously it is right here. There is a kinetic term conjugate to the variable phi and c, and there is this also nonlinear, the term linear in phi, which is called the joining term. It basically is joining two loops C1 and C2 into C. So it's almost like momentum space, some version of momentum space, and there is a fairly complicated collective potential, which I will not write. But if you find a minimum by 0, minimizing the collective potential, you will get the ground state energy of any theory. And then you study fluctuations. So this is a very standard logic. Once you take this collective field theory as seriously, you'll study linearize the fluctuations, and you'll get two huge matrices here, which is the mass matrix and the kinetic matrix omega 0. And it's remarkable that you can actually do those things because the number of loops grow. I don't know, Joao will show you how fast the number of loops grow. It grows exponentially according to the length. To do any numerical diagonalization, which is done in these works, you will have to introduce a cutoff. And this numerical work gave very good results for any value of coupling. So it is a very powerful method, really. But there is one word which explains why this is successful, and it's called stability, meaning you change this cutoff, which is the length of the loop which you included, to a higher length, and your results for the states do not change. So then you, at one point, see that it is kind of a convergent process with very high accuracy for those expectation values. So that is the comment on stability. That stability will play some role. Now, then we come to, so with those eigenstates, those are Those are the standard graviton eigenstates of a linearized gravity. I would give you spectrum. Or if you studied the vector model, where the corresponding theory is higher spin gravity, those would be all the states of higher spin gravity identically. Okay? So it gives a very good very good answer for the linearized eigenstates of both gravity and higher spin gravity. If you take those states, and Joao will show you the states, so I didn't use a transparency for that. If you take those states and sum it as e to the minus beta h, and those are not only states, those are oscillators. So what you get from that eigenvalue problem, you get the frequency of oscillators. So each oscillator will give you an infinitely many states. So you are solving by just coming to that matrix, which will give you the frequencies of oscillators. You are not finding one state, so a couple states. You are finding the frequencies of oscillators, which will then give you an infinite number of energy levels. So you take those energy levels and take trace e to the minus beta h, and you put those energy levels in, and you will get the free energy. And one of my former students, I pushed him to do that, and we spent 1 year debating the answer. What happened is the following. It gave a very good answer for t less than the presumed phase transition point Tc. And this was the answer in accordance with the loop gas, the ADS gas, which was already mentioned today. That was the outside of that black hole problem. It gave perfect answers for that. But as soon as you put in a value t greater than the presumed Tc, which is what you need to go into the black hole phase, you would get some nonsense. And that was the argument I had with Xianlong Liu. And he kept coming back saying that he did the correct calculation, but as he would change the cutoff of those lengths, the results was not stable at all in that region. So it says that there is something wrong with this theory, and it's not capable of seeing of even giving you consistent answers for temperatures precisely about that phase transition. So it was one reason why we decided to tackle the problem which follows, because if there was no specific reason, we would go happily, like in the past 40 years, using this collective field theory in a range where it gave beautiful answers. And this is where you meet the first challenge. And to understand then this other phase, it was realized that you should understand something which one would call finite n. Now, in that collective field theory, n was always finite, meaning there was a cubic term, loops joining, the prefactor was 1 over n. There was a quartic term, the prefactor was 1 over n squared. So we never really, we never were thinking of n infinite, that we used that Hamiltonian for perturbative calculations in 1 over n. Those were all correct for him, even agreeing with things such like two-dimensional string amplitudes, which is a highly non-trivial agreement. So those terms in the Hamiltonian, which are interacting and present with 1 over n, are taking into account. We didn't drop those. So what is there to be corrected? So there's something called finite n trace relations, which some of you know and some might not. And apparently you have to face up to that fact, finite n trace relations. And I must say this was pointed out first in a vector statistical physics discussion by Shankar and Yin. So there is a very nice paper on that, why these trace relations should be relevant to thermodynamics. And here we go. I can immediately tell you what a trace relation is. If we are dealing with matrices A, B, C, three matrices A, B, C, which can be basic matrix M, and A can be M squared, and B can be M cubed, and C can be M to whatever power. So any matrices which are 2 by 2, then there is this theorem, the Cayley-Hamilton theorem, which says if those were matrices of n equal 2 by 2, then this determinant, which is basically a Cayley-Hamilton determinant, should be 0. But what that does is establishes a connection between some of the variables. If you took A and B, those traces to be the basic traces, and maybe all of those traces here to be the basic traces, then from this equation, trace A, B, C would be a polynomial function of those reduced traces. So at this point, you say, if my n is a fixed integer, n equal 2, I better be starting to take into account these relations because my variables are not independent. And you might even wonder, and maybe even suggest, that that collective field theory is a nonsense. But if it's a nonsense, then why did it give agreement to high order in 1 over n with the modular invariant transfer of two-dimensional string? As you know, modular invariance of strings is a very non-trivial thing. The scattering amplitudes of strings are very non-trivial. So if you are making such a stupid mistake, why the agreement? You might wonder about that. I will not answer that, but provide basis so that one can answer that. But in any case, because of those trace relations, it's an obvious thing that we should impose those finite n constraints. And I remember, again, since we began doing this collective field theory, and especially in the case of vector models, and Joao was around, Roman Jacquet was bugging me all the time about this problem, and I typically would dismiss it. Now we are facing up to it, and unfortunately he passed away. But it took time to face up to that problem, which he really was bothered by, and that is some logic why you should be bothered by. So we set out with Robert to maybe implement the finite n constraint, and that's what all these papers are. That just take these relations into account. So try to build a theory which will be knowledgeable about trace relations, and you say it will not be making a mistake by overcounting and so on. But I should now go back and tell you the problem of black hole physics or quantum black holes or gravity is precisely that. Too many variables or a large, this is the problem of black hole physics is quantum black holes is a problem of large number of variables. You have this theory with infinitely many variables, which for that reason is also UV divergent. Many variables, and you are getting an entropy of a black hole, which is a very nice finite number, area over G. And there is a contradiction there, which actually is a contradiction. So I don't think it's not. It is related to this problem. What you have to do is explain how does the theory based on gravitons, which can be taken to any power in your Hilbert space, how do you reconcile that with the fact that in the same theory, you should have a finite black hole entropy? That's almost irreconcilable, except by this mechanism that I will now feature. It turns out that this theory is actually some beginning of a germ of an idea that maybe it's a very good theory, and it even knows about those constraints that should be put on it. You know that many theories, gravity, they have certain constraints and so on. They come directly from the Lagrangian or the theory. And this theory, likewise, this collective theory, which has only two terms, a kind of scaling term H2 and the cubic interaction between those loops. So think about just the cubic theory with interactions of joining and splitting. And if I need to have time, I could explain This is now schematic, gives you maybe some basic insight, but it is very general. Then comes some detailed calculations in specific models, which will be along the line and line up with what I'm saying. So that's the first theorem, that these trace relations, which I featured before, which are some kind of polynomial functions of those traces, are actually zero modes of this Hamiltonian. So that's where this Hamiltonian, even though it's infinite and you might think it's maybe incorrect, it actually is correct. It does have information about the trace relations in that form, that there are zero modes of the theory. Then you decide what you do with an infinite number of zero modes. There are ways to treat zero modes. Okay, so here is then the way we address then after that. Once we appreciate that, we are happy with, there's maybe some reason why the infinite Hamiltonian with infinitely many variables was successful so often, in fact, always below the phase transition. So here goes then the procedure, and this procedure which follows is painful. You say, let me look at those, begin looking at the trace relations, we classify loops along their length, and the number of loops grows very much as length, but we have to take a look at them. And as soon as we see, we have some basic set phi, which I will call gravitons. And we decide those are the basic set of loops. And we see a trace relations which is like that the capital phi is a polynomial function of the previous phi's. You obviously say this is not an extra variable, it's to base that trace relation. And that would just tell you eliminate phi as a change of variables or whatever way you want to do that in terms of phi. So that says that any variable which is function of the previous one should be eliminated. That's an obvious statement. What follows next is not obvious. There will be, and that is the surprise. And in a way, much of this discussion is about this equation. So much of this is that you will see some quadratic constraints that you will have, and there will be many. In fact, I should tell you that the number of these quadratic constraints will turn out to grow exponentially, e to the n squared. And because of that number, e to the n squared, that's why these constraints will be relevant for black hole entropy or something like that. But anyway, you see an equation like that, which is quadratic in psi and polynomials in phi. And you're first, if you are doing classical physics, you would say, I know how to solve a quadratic equation. What's wrong? I just eliminate these guys also. And therefore, I'm staying with a minimal set. I should say that minimal set is the one you all know. Actually, every experimentalist knows what a minimal set of singlet variables in a gauge theory is. You fix a gauge. You know, now standard discussion of Young-Mills theory or matrix model would not to go to this route to construct invariants, but it goes the route of fixing a gauge, use the gauge degree of freedom, and then you prove later that your calculations are independent of the gauge fixing term. That's a chapter in our field theory book. So you fix a gauge. So if there were D matrices, capital D, and there was one UN symmetry, then obviously if you fix a gauge, it would be D minus one matrices which are independent. And there is that many invariant variables using this trick of fixing the gauge. But this is something extra. This variable psi, it turns out that we have to keep them and not eliminate them. So that's the only extra knowledge I can tell you, that if you see the quadratic equation between variables, do not eliminate them. you are in the Hilbert space, and it makes some sense. You don't take a square root of A. That doesn't make, some mathematicians don't like that. So it's outside of Hilbert space. So there's some language which we use for not taking a square root of A. And even though classically you would eliminate such a variable, which is a square root of A, but quantum mechanically you will keep it. So you will keep this relation psi square. It will only mean that this psi can be applied on the state, but psi square should not be applied. So as far as the spectrum of in the Hilbert space, those are all phi's, any number of them, which are those basic set. We'll call them primary because the mathematicians call them primary. And this state psi, we originally, it says psi s, we call them solitons. That was the only connection physically we had, because you can have one of those applied on the vacuum, but not two, because this relation says 2 is equal to 1 times a polynomial of gravitons and plus other gravitons. So it's not a new state. So only this two. But there will be even other constraints which are higher order, cubic, quartic, and so on. So this subject of weeding out and keeping states in this Hilbert space becomes very, very, very non-trivial. And it turns out that it has been studied. So everything I said up to now, it was also identified by mathematicians. Namely, Hilbert was the first one that was famous for a theory of invariants. And those are just invariants under linear groups like Sn, Son, Sun, precisely the groups we are interested in. So if you are able to read some of those papers by Hilbert, that's possible. By Hironaka, already not possible. And Procesi is a god of this subject, and that don't try to read the paper by Procesi. And you should start with Hilbert. That's the best. But what you learned from reading it, that there is something called Hironaka decomposition in the algebra of invariants. And there are invariants of first kind and second kind. And the first kind act freely. That means those are our little phi's. Those are oscillators like the graviton. You can just apply the graviton any number of times on the vacuum. And the second kind, those do not act freely, but they don't tell you how to act. I commented on a couple of constraints like psi, which obeys a quadratic relation, should be applied on the vacuum only once, but there are then others that will change. So those secondary invariants will turn out to be some kind of Q oscillators. Q oscillators, probably some people are familiar with. It's a generalization of an oscillator where Q is related to 1 over n, an integer. You can only apply them an integer number of a certain power, and then you have to stop. The angular momentum is a Q oscillator because you go from the vacuum to state 2J, and then you stop in a fixed irreducible representation. So it has to do with group theory, and this also has to do with some group theory. Now, the number of primary invariants, if you have a d-dimensional matrix model, is the mathematicians also found it that it is d minus 1 n squared plus 1. It's an interesting anecdote that while mathematicians figured out everything, they didn't figure out that you fix a gauge. The thing which all our experimentalists know to do, fixing a gauge, they have no idea. So for them, this number d minus 1 n squared plus 1, which if I give you this number, you will immediately react, this is fixing the gauge. But for them, this was a big discovery. But we were hoping that they will tell us, so for us that was obvious, there will be this many oscillators that already appeared in, as I said, in experimental physics. But we were interested in knowing the number of the secondary states, which we call solitons. And that one, they were in the same bad shape as we are. So they didn't have any answer, even though they were very interested in that number. Robert will tell you about some ways of understanding the number of the secondary value. So I probably have to give some examples. Let's see, I am doing okay. I'm doing purposely slow.
7 more minutes.
Okay, good. So I still have to give you more examples because what I summarized was a general result. And I wanted to make a point that it is a result, a scheme, classification of states, which is also found by mathematicians. And another satisfying thing was the mathematicians also did this. They said, let's study just matrices of size n equal 2. Some matrices of size n equal 2, and then figure out the trace relations and so on, and figure out what stays. And then go to n equal 3, and then n equal 4, n equal 5, n equal 6, which is precisely what we did. And then they got tired out because the computers the problem became too big. So that's about the place we also get tired out. So the same limitation of kind of computers comes. But let's say n equal 2. So you would say the following: trace of x, so, and with two matrices, x and y, trace of x, trace of y, x squared, xy, y squared. You say n equal 2, probably I shouldn't include in this basic set anything which is higher than power 2, because you know that the Cayley Hamilton theorem will kick out, and indeed it does, because trace of ABC will be related to the product of lower traces. So indeed you find that trace of xy squared is a function of those 5 polynomial as I described, and trace of yx squared is again a polynomial function of those. And at this point, you think probably there will be nothing left, and at this point you might decide to stop. This works perfectly with that formula, d minus 1 n squared. All higher length traces can be expressed in terms of this basic set. For this case, n equal 2, and k equal to, k will label the number of matrices. But if you increase the number of matrices by 1, okay, yeah, 3 matrices, okay, 3 matrices. You do the same. I just want to tell you that some of the understanding of this is very elementary. It is more the complexity which starts to grow as you go to higher n. If n is 2, but 3 matrices, trace of x, trace of y, trace of z, each one, these are all up to length 2, trace xy, trace yz. Those are your basic gravitons. And then you come to the trace of xyz, which is length 3, and you find that indeed looking at the Cayley Hamilton theorem of the total length 6, which would involve 3 squared, or square of this word, the words of length 6, you'll find these relations, that this s squared, that's what I was claiming before, that we will run into such thing very soon. S squared is equal to this polynomial function of those basic m's. So those are the basic traces. Those will be the graviton oscillators. And S is, at this point, you say, oh, this must be a solitonic state, meaning that S can be applied on the vacuum once, not twice. This soliton is a fermion, and I'm happy. But it, as I said, it gets more complicated than that. That would have been a simple answer for this Hilbert space, that there is one state S applied once, and we maybe shouldn't even worry about this is just another sector of the theory. And then further, I wanted to Maybe I wanted to show some longer, let's see. Do I have a lot? I think I lost the main formula. I still wanted to impress you with a one-page formula, which will show some huge number. And obviously, the number, these numbers grow rapidly. So this becomes a page. And then I should switch to some other counting of these things. This is 3 matrices. Yes. Namely, there is certain knowledge about the number of the states, which comes from knowing the partition function at finite n for certain matrix models. This method was pioneered by Bo Sandberg and then repeated by Acharoni and company, voila, in a 100-page paper. And that method allows you to calculate exactly if you are dealing with matrix oscillators, the partition function, trace of e to the minus beta h. So that will know about all the states which come into the construction. And if you look at this partition function, which was known for a long time, it takes the form of a ratio, e of x, a polynomial of x is e to minus beta. This is x, e to the minus beta is x. It takes the form of the polynomial of x divided by another polynomial of x. And if you look at this polynomial of x, the denominator is coming obviously from oscillators, bosonic oscillators, each one, oscillator J and the degeneracy C will give you this contribution. So those are those primary states, which I said can be raised to any power in the Hilbert space. They can give an oscillator contribution. They are the gravitons. These states which can only be applied a couple times are the secondary states. They will never give you an infinite sum. They will never give you a denominator, and they will only appear through this. So there is a very clean separation of that algebraic theorem of Rossesi. There is and Hironaka. There is a very clean correspondence between these two. So from here, you will learn what the total number of these states is. But again, this partition function can be evaluated only for n equal 2, 3, 4, 5, 6, and then you get tired out, much like with the previous procedure of dealing with those constraints and so on. We don't have an exact answer for any fixed n and large n, but for those values low n, we have this answer. It's in precise correspondence with the numbers and the degeneracies of those primary, that's trivial, but secondary states, which give you the numerator in this formula. So that agreement tells you that, yes, you should have included that state, even though it's constrained, and you might have kicked it out, which had a quadratic constraint saying s squared is polynomial of phi. You definitely should include it because this independent calculation of partition function by this unitary integral says it should be there. There should be at least some state at that energy level. So there is a perfect agreement for this decomposition of states with I keep coming back with these formulas. By now you got the idea. Here there are some more states. In this case, this is n equal 5. I guess I brought it up just to show that this polynomial, which is up in the numerator, so the denominator are the graviton states. Their number is pretty controlled. The number of graviton oscillators was d minus 1 n squared, very linear function of n squared. But these states grow rapidly in number, especially the total number. The degeneracies are huge. And the number of states totally will go. For example, at this n equal 5, now you remember at n equal 2, we had only one state, which is of this kind. Now we have 15,424. So this is that number, and it is that number which is basically the big discovery. I should say the following. The famous phase transition comes from the numerator and not the denominator. So when I was forcing my student to keep calculating this denominator and keep even cutting it up artificially in accordance with the so-called stringy exclusion principle, which was I learned the stringy exclusion principle, famous work of Mandelstam and Strominger, that would instruct us to cut down this denominator at certain length, and you are home free. We just exclude those loops which are over certain length. That would mean just working with the denominator, but that never causes a phase transition. It is the numerator which causes a phase transition. There is a famous theorem of Li and Yang, which says if you look at the zeros of the partition function, there is a famous Li and Yang version of a phase transition. You will get the zeros in the complex plane, which will coalesce precisely around the phase transition point. So it's a very obvious connection between the numerator and the phase transition. And calculating anything along the line of the denominator will not tell you. But so that answers why these states are already relevant for even observing a phase transition in this theory. And then,
So,
yes.
and that m equal to 2, it was the number of matrices for this matrix.
That's right, yes. And remember I said, oh no, little d is the number of matrices. That's the number of dimensions in a Young-Mills index D. And n is the size of the matrices. Sorry, those two, there are only two numbers. One is the number of matrices, and we call it D. And then the size of the matrices is n. Yeah. Yes.
So in the previous slide, is there any understanding of why those polynomials are palindromic?
There is some, you can prove that theorem also. It's in our paper, and Robert was able to prove that. There is some proof which goes back to some duality properties in exchange of T to 1 over T in these matrix models, which kind of is a remarkable property, similar to some property of strings, duality of R to 1 over R. Yeah.
When you say Schumburg did this for large N, do you mean that he knew about these secondary invariants?
No. In this, that is a method which is valid only for three cases. And there is one extra U matrix. That's the matrix which imposes the singlet constraints. And you can integrate out the quadratic Gaussian matrices, and you get an effective U model. And that U model you can study for large N. Numerically, you will get the answer. The free energy is 0.05. It doesn't tell you where it comes from. So we studied that first, but didn't help us anything to understand anything. But you could then plot that curve, and that's all. And you could estimate as you change n that it is proportional to n squared, and then you get the curve. But it doesn't tell you where it comes from. So this is basically an analysis. Where do the states go? What are the states which will give you that curve? So, and now since as I said, we know the number of these primaries, which is, again, I want to emphasize, for us it was a trivial number. For mathematicians, they figured it out numerically, but not analytically. Okay. But for the secondaries, we looked numerically then, because here are, for these special cases, here are the growth of those secondary invariants. We had for n equal 5, it was 15,000, and then immediately next you have 300,000, and then a couple of billions or whatever. So the number grows very rapidly, and then if you plot this curve versus e to the c times n squared, at least for this many values, 4, 5, 6, 7, that's not a big number of n's, but at least it agrees with it. It's fairly good agreement, and you can deduce that number coefficient to be 1.1 over there. So that It doesn't look like there is an analytic answer to that coefficient 1.1, but you never know. We didn't get some conjecture on that. So this is the growth of this secondary state. So vaguely, you might say that this number of states, especially if it was some kind of fermionic problem, this is a finite number of states, which you can interpret as a contribution to the entropy, which is finite, while the other states would contribute to the entropy, but in an infinite way. So this reduction of the Hilbert space to these states rather than oscillators results in this kind of finite entropy. Working with two of these. I should say that there is much more. You can study them. You like to understand the structure of this Hilbert space. And I think on this, I don't have much time. Neither do you like to see another series of complicated states. But if you simplify the gauge group to Sn, for example, which was studied in this paper with Robert and Kemp. Yeah. No, this is not. Yeah. So if we study Sn, we could understand the structure of those secondary states completely, even for arbitrary n. So that was a big progress in a way. And it follows the following pattern. For example, the state 1,1, which is secondary, is a bit one of this here are some basic states of the secondary. And then comes multiplying them with some other fixed states. But those multiplications, which starts to build a full Fock space, but stops at power 7, and then 7, and then 6, and 1, and 1, and 6, and 5. There is some pattern, which I said before. It's not just that you can apply an oscillator twice, and now you are, that's the, all the states are Q equal to oscillators. This would be the pattern, which you can take a look if you figure out how does that work actually. We know the answer, but we don't know the theory of this. Now, one can study SN models and then also vector models. They were also studied already in this paper by Hendrik van Zyl, Robert. And then you can start analyzing the Hilbert space. I should say for the vector model, which is fairly complex, so there is some other way of understanding the Hilbert space, which is in an earlier paper I wrote with Shumit Das, which gives you the finite number of states by group theory. Yeah. So for that case, we have another technique to understand the states. So at least in the case of Sn, we know the precise structure of this Hilbert space, not only for some cases n equal 2, and n equal 3, or n equal 4, and for vector models also. But for matrix models, that's maybe an outstanding problem to have some mathematical structure of those states. So with this, I think I'm ahead of time. And some of those will be also discussed by Robert and Hendrik. So just to summarize, we have identified the Hilbert space of finite n matrix model. And I just want to stress that in a way, we always were doing finite n, just that we have done it approximately before. We always were doing large n, but n was finite. It was never infinite. Just that it worked with some naive techniques. It only worked in certain sector of the temperature phase. We identified the states which allow you to explain the entropy and the free energy in that phase of the confinement. And most relevant are these additional secondaries. And even more relevant is their number growing exponentially in n squared. And the fact that they shouldn't be surviving, they should have, basically they would be eliminated but quantum mechanically they stay. So it's a real quantum mechanical effect. The reason they are so. They survive and they are totally oblivious to that stringy exclusion principle, which you should not take seriously. Meaning they violate the stringy exclusion principle and they are still happily there, not worrying about stringy exclusion principles. And so they are candidates of microstates. So finally, let me comment on the nice work which also went on, which everyone is aware of, on fortuity, looking for states which are outside of the graviton cohomology and with success. In that work of Chang Lin and Yao Kim and his collaborators, which there are a number of nice papers, those were in supersymmetric theories. And there again, studies are for n low. So I'm not sure they went up to n equals 7, but okay. And n is low. That is feature of both of these studies, that we are studying things at low n, but nevertheless implying things for large n, which is what we are interested in. So those are called fortuitous state. I should end by saying it's not clear that the states we are finding and they are finding are absolutely the same, that there's something has to be understood. So maybe Sam can illuminate that. Maybe we have to discuss that. Maybe they're the same. I gave a name miraculous to our state, or I actually suggest that to be the general name, because fortuitous, I'm not sure. There is nothing fortuitous in being a black hole microstate, they just doesn't fit the subject. That's a joke, really.
Yes. Yeah, get it.
So this is a good question, but so you mentioned the SN model, and I think so there, if I've understood correctly, we know the form of the primary operators, I think almost immediately, but for matrix models, is that also true, or do you have to compute the partition function first and then try and sort of see at least what the primaries are?
Even primaries, you have to see which states are primary. You don't know it directly. So by comparison with the partition function, and then identify at least what length they should be, and then you calculate.
See, and then you would look at the denominator.
That's right. And then you look at the denominator, you look at how many dependents you need, and it's actually not unique.
It's not unique.
Because you see, there's one equation like that, trace A, B, C, and trace A, C, B. Those two don't commute. So those, if you take one to be primary, then the second one must be a second.
More question.
Yes, question.
So you said that's coefficient 1.1. Okay, we don't know where what it depends. It depends on D, I guess, right? On the number of.
That's right. Yeah, but that's what's equal to.
That's not just equal, but you get a similar coefficient for other.
Right. I'm sure. Yeah.
But you want to identify that with what we see from the planet. Or ideally, right? That's the n squared term.
Indeed, that would be the coefficient.
There might be some alternative for knowing that
from gravity, but we are in very primitive set of models at this point. These are actually, so the analysis is kinematical in a way, apart from the fact that it works for the oscillators. Because these trace relations are kinematical, they are not dependent on the coupling. But it doesn't mean then you have these states, that's now your Hilbert space. In that Hilbert space, you have to work out the solution to the interacting theory.
Yeah, that's my next question. So if I want to think of this in n equals 4 or something, then have a potential.
Then it will rearrange the states as perturbation theory does. You have the set of basic states, that's your inverse space. Will not stay precisely the same. There will be a linear rearrangement and high ordering coupling constant. But the number of states and some of these properties that cannot be applied to space. All of them. So that must stay. So some of the basic properties must stay.
So, okay, so you mentioned that so for these primaries, there's sort of also a gauge fixed perspective on it, right? So
that's right. Standard
with this gauge fix, we obtain,
and that gives to that number p minus 1 and squared.
Is there any way of also thinking about secondaries in a gauge fixed?
Not yet.
It's yeah.
It's more than oh, in fact, if you think of gauge fixing, then you are
discounting
like an equation for you're losing precisely those important ones.
The fact that it goes like to the n squared so suggests that somehow maybe in some gauge fixed matrix you can think of it as the matrix entries.
Gauge, so that is a misunderstanding. These secondaries are states. The primaries are oscillators. Every oscillator has an infinite number of states.
Yeah.
So actually, there is many more primary states than secondary states because each primary oscillator, and that's why they summed up the denominator. So it's important to distinguish that those what we call secondaries, those are states.
Sure.
Now, some of them are getting close to an oscillator because I think the power up to 7 or up to 120, depending on n. So they are almost would-be oscillators.
But yeah, okay. But at some fixed energy, there are way more secondary states than there are. Then you could make using primary.
That's right. That numerator is that very large.
Yeah.
Plug in a fixed energy, that numerator will be. Actually, I forgot to mention the theorem is that that coefficient P is positive. All those coefficients are positive. Even that is not true. Most of the examples of partition functions which were brought in this form P and Q, you have negative terms. So we had to bring this in. So there is a theorem that you can bring the partition to positive form. That's important. Otherwise, this comparison would not make sense.
Okay, great. Maybe one more question, one last question. Okay, so seems like there are no more questions, so thanks again for a very helpful. Same place. On top of the same way. I am at the first. She would have known you.
Because you won't be able to reach your buttons otherwise.
Yeah.
Okay, so before we start, let me make an announcement about this voucher. So this voucher is valid for 3 years. That is 750 Rand. So first thing you need to do is take a photo of this voucher. If you lose it, it shows what. So you have to show this to the place, the store, and they scan this. So the entry is there on the system. Better. And keep an eye on the tab, how much money they are deducting. Now, I mean, this is valid for 3 years. Suppose you are not planning to go back, you give it to a student or somebody. And let them use of the meeting. So it's legal.
They'll stop you at the border.
Then, so the stores are open roughly from 9 a.m. till 9 p.m. On weekends as well.
Which stores are these?
Only at Nielsen. Only at Nielsen. Okay, this is valid only at Nielsen, not at Checkers at Nielsen. So all other coffee shops.
We have Day1.
Right. Okay, so that is the announcement. Okay, so the last talk of today is by Joe is going to talk about large and master field optimization for monthly matrices.
Thank you. Well, thank you, Anosh, for the invitation to give the talk. So there's the title of my talk. Right, I have a plan of the talk, but as you can see, there's several pages, so might as well move forward and see how far we get. So the first question is, why are we considering matrices? I think there's some students here, maybe already some senior ones, but others less so. Well, basically, our standard model of particles is developed on the basis of matrix valued theories. For the electroweak interaction, you know, there's an SU2 cross U1 symmetry. So your gauge field, A mu, is a 2 by 2 matrix. And for QCD, color degrees of freedom, as I think hopefully you will know, the gluon is a 3 by 3 matrix valued gauge field. So, for instance, if you then put together into a gauge invariant Lagrangian, so-called pure QCD, so that's just gluons interacting amongst themselves, then you should be able to get that theory should itself be able to set lambda QCD and predict global masses. If you then add quarks or matter fields, then you expect in the so-called chiral limit to establish confinement, get meson and baryon masses. So this is kind of the older fashioned motivation, which we'll come to just now. Perhaps of more recent interest, there's n equals to 4 super Yang-Mills theory, which I call is a QCD cousin, which is essentially a compactification of n equals to 1 in 10 dimensions down to 4, as a result of which you then have a number of scalar fields. There's beautiful properties once you have this supersymmetry added, the fermionic degrees of freedom added to that bosonic sector. This theory has remarkable properties. Costas can tell you all about it, integrability, and so on, and so on, and so on. Right. So we started off with 3x3 matrices and 2x2 matrices. So why are we now talking about large n? In other words, instead of having 2x2 or 3x3, we now have n by n, and to make it even perhaps less plausible, we're going to take the limit as n becomes very large. Actually, in this work, strictly infinite, so that I stay in the good phase that Antal was just explaining. So anyway, so this goes back to the work of Luft. What is that, 50 years ago? We generalized 3x3 matrices into n by n. The motivation is QCD. QCD is a theory that as you separate quarks becomes very strongly coupled, so you cannot use perturbative methods such as that are so successful for QED. So there's no perturbative parameter. So this was an attempt, I would imagine, initially to establish some kind of parameter around which you can then expand. And that expansion, that parameter is 1 over n. So basically what the suggestion is to generalize to n by n matrices. You rescale your coupling. So you introduce what's called Struft's coupling. Lambda, which is g angle squared times n. You take n to go to infinity, but make sure that lambda remains finite. So then what you observe, so you now have matrices that propagate. So the propagators from that point to that point, it's described by 2 indices, so they look like a double line. And this is the kind of Feynman diagram that you would get typically. This one turns out has boundary, if you want to call it, of vector fields. Vector fields transform in the fundamental representation of the group, so therefore they only carry one line. But you see that as you start to develop perturbation theory, you can generate objects or diagrams that start to look like this. In this case, as opposed to that one, there is a hole, or it is it should be a surface of genus 1. So what Tuft showed was that if you make sure that lambda equals to g squared n is fixed, you take n to be infinity, then the expansion in 1 over n organizes itself in terms of surfaces. So you could say that, so for instance, the ground state energy, the leading so-called planar approximation, which is all the surfaces that or have typically either fall on a plane or on a sphere, goes like n squared. There it is. And then as you go to the next order, goes like 2 minus 2g, where g is the genus of the surface. So the energy you expect it to be n squared plus a term that is independent of n. And of course, that will, each term will depend on the coupling constant. So that's, I guess, the first hint, since you have Riemann surfaces, that perhaps there's a stringent description of QCD, something that is still an ongoing project. Right, so I think we all know that you cannot observe quarks. They come in bound into mesons or baryons. If you only, so that means that we should be looking at invariants. Now, these are local gauge theories. So what are the gauge invariant states? And maybe we should then be looking at restricting to gauge invariant states only. So for pure gauge theories, the invariants are what are called Wilson loops. So you take some closed contour, take a path-ordered product of e to the I times the gauge field. If you want to add matter, you have open strings. In each end, you've got a quark or an anti-quark. So you would have here a string of gluons extending between point x1 and x2. There is a very important property in the large n limit, and that's called the large n factorization. So if you look at the ground state expectation value of the correlator, say, of a product of two gauge invariant states, then you can show that as n goes to infinity, that's the product of the expectation values. So and then that's not the case normally if you have correlators, but that's certainly true when n is equal to infinity, and then the next corrections will come of order 1 over m squared. So that suggests that perhaps there is a possibility of formulating the theory directly in terms of these gauge invariant objects, and this is what I'm going to describe. Okay. Yeah.
So you've seen SE2, are they non-intersecting loops?
It doesn't matter as long as they are gauge invariant. The leading
intersect.
they are
intersecting the Eisenhower.
Nice.
There are systems. So Eisenhower would have non-existent.
So I think Antal has already hinted or mentioned this, that this observation led to the so-called formulation of the Migdal-Mackenzie equations, which are essentially a form of Schwinger-Dyson equations. So I'm just going to schematically introduce here two operators that are operations that are relevant to what comes next. And this is going to tell you what that box acting on the loop is that you asked Antal. So the idea is to make things more regularized, you have a lattice or two-dimensional lattice in this case, and you have a loop. Okay, so that's where you, as you know, you introduce the gauge fields in a link. There is an action that is called the Wilson action, that is the sum of what so-called plaquettes as you go around a little square in the lattice. So if you start with a loop, and that's the link that we're paying attention to. So when you join that with the action, and as a result of which, if you get two contributions, one where the loop is added in that direction, and one where that link is subtracted. So that operation will be the box operating acting on the loop at that point. Okay, and that is equal to another type of operation where if this is a self-interacting loop, if the two links cross in the opposite direction, they split, and with the same direction, they split with a minus sign. So this these are called even today loop equations, and there was great hope that if you can somehow handle them and solve them in some way, you essentially would have managed to solve a large N UCD. Right. So now I'm going to describe then the collective field Hamiltonian. Antal, Biavitsky, and Sekita. He just schematically showed it to us in the previous lecture. I'm going to give some more technical details. And it comes out of the observation of the question that is then the large, if there is factorization, is then the large N limit semi-classical. So what the collective field theory Hamiltonian then is that it gives you a framework that essentially establishes that this is the case. What is the philosophy? So this Hamiltonian is just summarizing what it does. It's an exact rewriting of a theory in terms of its gauge invariant variables. And then as we will see, the large N planar background is then obtained semi-classically as the minimum of an effective potential. And then you can expand systematically about this large N background. You generate cubic terms, as you saw. And this in examples that have been handled and treated very carefully over the years, all indications are that this generates the 1 over n correction systematically and completely. So as long as we stay in the right phases that Antal, and which I think so well. Right, so what's the idea? The idea is to implement a change of variables from the original variables, in this case, the gauge fields. I'm just going to call them X with some big subscript A, to the invariant set of operators that we call, these are the collective fields, which we'll denote by phi of C. And then you require explicit hermeticity of the collective field Hamiltonian. This change of variables is accompanied by a Jacobian, called a J. Now, the insight in this method is that in general, J is not known explicitly, but if you require the Hamiltonian now to be explicitly emission, then you get an equation. So this equation looks a little bit complicated and out of thin air, but basically what it does, it's got a derivative of the Jacobian with respect to psi, the loop, but it also has, then there are two elements, okay, that I need to emphasize. There's a matrix, a loop-valued matrix, capital omega here. So this is summed over C prime. So this is capital omega, and there's a vector valued in loop space, little omega. Okay, so those are two operators or two that I will describe in general. And as we will, as we'll see, essentially this is going to be joining two loops, and this is going to be splitting one loop into the two. So these correspond to the operations that I showed you when I discussed or showed you the Migdal-Mackenzie equation.
Well,
Yeah.
Is that map unique?
It's the map unique. So as long as, so Antal has referred to it as an overcomplete set. There are these trace relations, but the philosophy that can be used is that these trace relations only occur if you have two n by n matrices. They occur for matrices of dimension n plus 1. If you imagine that you take n to infinity, you can argue that they are complete. And as I said, there is a lot of work that has been done. That's sure.
Any satisfying. You know, in field theory, we have a definition theorem, meaning you can change your field phi by any function as long as it perturbatively, okay? And you'll get the same S matrix. I guess that's all I get. Know the name of this theorem. And the S matrix of the theory will not change if you change fields. Any function you can take. Free field theory. And change phi to psi squared or psi cube looks very complicated. You compute the S matrix and you get 0.
Yeah, with perturbative.
Yes, yes. So this is perturbative in 1 over n.
Okay. Yeah.
That's
So I'll give you some examples as we go along of what this loop space. Okay, so anyway, what is this matrix capital omega C and C prime? There's the definition. And little omega, there's also the definition. But in terms of the loop structure, what it does is what I've already hinted. So capital omega, you start with C and C prime, and you join them into a sum of single loops. Whereas this one splits a given loop into a sum of two, or in general, smaller loops. So I'm going to give you some examples. Anyway, so requiring this kinetic operator then to be explicitly emission, yields the equation for the Jacobian in the previous slide. You plug it back into the collective field, into the Hamiltonian or the original kinetic piece, and one obtains the collective Hamiltonian. And I'll present its form just now. All right, so some example. I think Palab has talked already about the single emission matrix. If you have a potential that only depends on single traced moments, trace of x, trace x squared, trace x cubed, and so on. In this case, there's a UN symmetry. So things only depend on, so you go from x that has n squared degrees of freedom to the eigenvalues. So the theory can then be this. So the Jacobian would be the change of variables from an emission matrix to its eigenvalues. That's, in this case, it's well known. The Vandermonde determinant, and so on. So essentially, you go from n squared to n degrees of freedom. So in that case, there are many types of invariants you could choose. The trace of x to the n. You can, the trace of e to the ikx. There's the expressions in terms of the eigenvalues if you're interested. Then Fourier transform, and you get the density of eigenvalues, which becomes continuous as n goes to infinity. Right. So just to elaborate a little bit, I said this capital omega. So you start with a loop phi n, and another loop phi m. You combine them. This is what you get, a loop of length n plus m minus 2. Little omega, I said, splits into 2. So there's the explicit expression that you would get. Yeah. Right. For D matrices, which is the kind of the systems that I'm going to be interested in. So the UN invariant loops are single traces of products of the matrices. So this loop space structure is now much, much more complicated because you can take trace, we have x1 to the m1, x2 to the m2, then x1 to some other power, x2 to another power, and so on and so on and so on. Remember, matrices do not commute, so only up to cyclicity or some of these the same. So if you have two matrices, you can represent 1, 1 is the trace of x1 squared, 1, 2 is trace of x1, x2. Due to cyclicity, that's the same as 2, 1. 2, 2, trace of x2 squared. And you can see what the structure very simply in this case. Okay. Antal also mentioned, and there have been some questions about vector-valued fields. In this case, the natural invariants are bilocals. So if you have a field that is, there's an index, you can call it a color index A, goes from 1 to n. In this case, this is the ON vector field. So you choose two space-time points, sum of A to n, that would be a bilocal. Okay. So there are some of the examples of the kind of invariants that we would consider. So you can always rescale the loops by an appropriate factor. Yeah.
In the previous slide, how is phi and phi k is related?
How is?
Phi and phi k.
Yeah.
Yeah, this one and the last and the third equation.
So phi of k is the trace of each of the ikx, which you can write in terms of eigenvalues in this way. Happy with that? And if you do a Fourier transform, you get the density of eigenvalues.
I see. Okay.
Okay. So which in the large n becomes nice and continuous and so on. Okay. So the key point then, so this is the form of this collective field Hamiltonian. You see that it has a kinetic piece. So this is the canonical conjugate. These are canonical conjugates to the loops, plus an effective potential. Now, the key point here is that this kinetic piece comes like 1 over m squared. So if you think of simple quantum mechanics, it's like having a mass that goes like m squared. You're taking the limit as the mass goes to infinity. So basically that means your particle does not move at all. The first thing you need to do is to find the minimum of the effective potential, and then you can expand and calculate fluctuations. So what is that effective potential? There's the form. Okay, so this is the vector valued omega c, the inverse of this capital omega, and then little omega. So it has this matrix. You have to find the inverse of that, and then multiply through transpose omega minus 1 and omega. Okay. So there are some subleading terms that we don't worry about in this work, but they are well known. So there is what is the, immediately you can see the possible use of this approach, which is that if you have a collective field Hamiltonian and you truncate the loop space, so you have products of matrices up to a certain number of matrices, call it L. then you should be able to get a large N limit in principle by minimizing the effective potential. So this was already something done a long time ago. We applied it to 2+1 lattice gauge theories with the Wilson action, where we take products of unitary matrices using the action of the day. So what was found is that, and it became known particularly in studies of single unitary matrices, is that unitary matrices have a phase transition between a strong and a weak phase. In the weak phase coupling, in the weak coupling phase, the minimization, you can't just minimize that with respect to the loops. That has to be done together with a constraint that this matrix capital omega is semi-positive different. So this is now we're going to be dealing with emission matrices. Effectively, you are always in the weak phase. So that is a constraint that has to be taken care of. Right. So that's all work. But it turns out that these constraints have, again, been, I call it, rediscovered by Krutensky, Martin Krutensky and Anderson. I'm just going to display the simplest display that they have given to that is imagine that you have, so again, imagine that you have discretized your two-dimensional lattice here. You take a loop going from x1 to x2, and then the loop going again from x1 to x2. So if you consider an arbitrary set of coefficients, you define A to be a sum, so of all different ways in which you can go from x1 to x2. Since the trace of A dagger is always positive, non-negative, for any CL, you get this condition. So remember, you're now going UL from here to there, but then U dagger is in the reverse direction. So essentially, you have, if you form this matrix L and L prime of trace U dagger to the L, UL prime, this must be, again, non-negative, semi-positive. So this has now been used in a recent program that goes by the name of Bootstrap. Essentially, it can either be used in terms of parameter scanning for loop equations or using semi-definite programming. So these are some of the papers, original papers that brought us this interest. So Henry Lin, we did this for loop equations, then Hartnell and collaborators for the Hamiltonian approach, then Kazakov and Zheng, that then applied it to some theories already with the Young-Mills coupling. And with Robert and Antal, we kind of revised some of our previous approach, but that's now based on the optimization that I'm describing. So this other work goes by the name of numerical bootstrap, and it has, and there's been a fair number of work done using that approach. Okay, so what I call this matrix of inner products here can be shown that is directly related to the loop matrix that I have. So the requirement of requiring capital omega to be semi-positive definite is equivalent to the requirement that these type of objects are also semi-positive. Okay, right. So I've been talking about, in principle, about local gauge theories. But what I'm really going to be doing is discussing a number of systems with only 2 matrices and 3 matrices. So why should we have an interest in considering systems of only a finite number of matrices? Well, of course, there's work that was done a few decades ago. I mean, Lorenzo was describing to us how to compactify things in a much more sophisticated way than the original work in which you just put UCD on a box. Okay, but if you do that, basically it's like compactifying, and you reduce, you get Young-Mills theory on a torus. There is very interesting, this is still something that people look at. Neguchi and Kawai show that if under assumptions of some symmetry not being broken, that instead of having loop equations for an infinite number of unitary matrices, each one on each link of a lattice, if you just consider 4, you get equivalent loop equations. That turned out to be a little bit too naive. We've got a quench, and then this was generalized for emission matrices and then for the Hamiltonian. So this is kind of a little bit old-fashioned motivation. But as I think most of you here know, with the development or discovery, whatever you want to call it, of the brains, systems of finite number of matrices have a new kind of physical meaning. And particularly, there's the famous BFSS system that says that you have the supersymmetric quantum mechanics of 9 emission matrices. So you basically reduce to compactify 1 dimensions. These are systems, these are D-nodes. Then that provides possibly a definition of M theory or string theory. For the path integral, this was generalized by IKKT. And then of course, this was followed by the whole ADS CFT program. And in particular, I want to emphasize the so-called BMN, which essentially what in the so-called plane wave limit, the scalars that I mentioned in n equals to 4 super Young-Mills, you can have scalars moving in a C if you want of one type of scalar. And that interaction, that propagation is described by an Hamiltonian in terms of a finite number of matrices. And there's more recent work or interest, of course, which remains as in terms of black holes and matrix quantum. Okay. So what is it that I'm going to do? Let's see how bad I'm doing with time. I normally always run late. Okay. What is that? So I'm here. I'm now just, giving you results coming from that work that was done by 2 previous students of mine at the time, one who was my postdoc. And this is the system that I want to consider. So I have 2 emission matrices. So this is the Hamiltonian version. So this is just momentum squared. But then I have a Young-Mills interaction between the 2 matrices. Now, notice that one of the motivations, there is another one that I'll mention later, is that I don't have a mass there. That's done on purpose because I think dealing directly and numerically with systems that do not have masses, typically Monte Carlo and so on, these tend to be unstable. And what you do is you switch on a mass and somehow you extrapolate down to mass equals to 0. But what I wanted to understand is we want to understand the large n limit of the system numerically. Does it make sense? Is it stable if I immediately switch off the masses and see what happens? Okay. My convention here is a little bit unusual because I've divided already by 1/n, so the tooth coupling is really G Young-Mills squared in this. Okay, so we have seen, so what we want to do is study the system in the large n limit using the collective field theory expressed in terms of invariance. I've already discussed a little bit what these invariants look like. And again, I've already also indicated in this case, I'll give you precisely what the rescaling is, what the collective field theory Hamiltonian is, and the effective potential then, it's like a centrifugal term that gets added if you're doing regular quantum mechanics. This potential is the Young-Mills potential, but it gets added to that term. Right. Okay. So what is then the large N background? Then we've discussed that the large N background is the minimum of V effective, but it has to be subject to the constraint that capital omega is semi-positive definite. You can see that there is a problem if you've got to take if this develops negative eigenvalues, this will quickly minimize to run away to minus infinity. So that's one kind of practical way of understanding that. So what is it that we do? We start with some maximum, some length. Let's say you have for L greater or equal than 4. Let's say you start by taking loops up to length 4. So you truncate it. So capital omega then has a certain size that I call then omega. But omega itself, however, depends on loops of lengths up to 2L minus 2, because remember, you're combining loops. And we saw that there's two derivatives, so you get 2L minus 2. So even though capital omega has a certain size, it is a function of a larger number of loops. So I call that the number of loops of L max or V or less than V effective is a function of all those loops. Let me just give you some idea. So basically then, that's the truncated version of the effective Hamiltonian, the effective potential. So you just sum for CC prime up to what I call N omega. That's the term, but capital omega itself depends on so-called L max. Okay. So this is how the number of these loops grows. This is for two matrices. If you see that you have L max equals to 8, this is the size of N omega in the total number of loops, and it grows very fast. So if you've got 14, size of the matrix is these are 93 by 93 matrix, and it contains 2,615 loops. I've highlighted that because that's what I considered in this particular project. Okay. So finally, how is the constraint enforced? So there is the bootstrap method, semi-positive programming. Here we go back to an idea that is essentially to introduce master variables, which are very similar to the original variables. So you see that if you want to minimize this effective potential subject to this constraint, you can introduce any variables that explicitly satisfy the constraint. So you see that this is the form A dagger A, so this is always positive definite. So in our case, to be definite, to be precise, we're going to choose X1 of the matrices to be diagonal. Next two is an arbitrary n by n emission matrix. Basically, we factor out an overall or global, if you want, univariance. Master field then has n squared plus n real components. And those are our, so we then carry out minimization with respect to these master variables. So there it is. So we use standard minimization routines. Once you converge to some configuration of x1 and x2, you plug it in back to get the values of the loops. Now, so the planar background then is specified by the large N expectation values of all gauge invariant operators reconstructed from phi. Okay. So in this case, as I've mentioned, I've chosen a truncation with L max equals to 14. There's 2,615 loops. Capital omega is a 93 by 93 omega, so matrix. So at every step of the optimization, you have to invert that by the other. For the master field, we took n. to be 51. So these are 51 by 51 matrices. One is diagonal. The other one is generic emission, which basically means there's 2,652 master variables. So we try to keep these numbers to be similar. Okay, so let's go back to the theory that I said I was interested in, which is the massless. It's the quantum mechanics of two massless matrices interacting via the Young-Mills interaction. All right, so this, in addition to the fact that we're considering strictly a massless limit, there's something that's very important in this theory, and that is that there is only one dimension and that's G Young-Mills. So G Young-Mills in this case has dimensions. There it is. It's in 3/2, and the fields x1 and x2 have dimensions -1/2. There's nothing else. So what does that mean? It means that for instance, any energy that I have, any physical quantity with an energy dimension has better scale like G Young-Mills to the 2/3 or tooth coupling to the 1/3. Trace of x1 squared will have to scale like G Young-Mills to the -2/3. Any quartic correlator will have to scale like G Young-Mills to the -4/3. So we wanted to understand how does the numerical approximation respect the scaling, and together with the fact that it's directly in the massless. Okay, so we considered it for different values of G Young-Mills, so they listed there. So this, so working directly in this massless limit, the optimization exhibited remarkable stable convergence to the system's minimum for all GNM. We had no problem whatsoever with convergence for all this range of G Young-Mills. And let's see how so this is the raw data. So for instance, if I look here at the value of the ground state energy, remember, this has to go to like m squared times something that is finite. So that's E naught over n squared. That's how it looks like. Okay. So now we expect it to behave like, or to scale like some constant times G Young-Mills to some power P. What you want to know is how well does the value of P, so what is if we do least squares fit to the logarithmic plot, so it becomes a straight line, we can get what is the value of P that comes out, that fits the best least squares fit. And this is the kind of value that we get. So, yeah.
Question. This is a matrix quantum mechanics.
Yeah.
And you're considering this as zero temperature.
Yeah, there's no temperature here. This is no temperature. I haven't introduced that. Okay. So remember, we expect this to scale like G to the 2/3, and this is what you get from the least squares fit to the. Okay, so that's pretty accurate. This is the linear fit that is shown below. So again, so the accuracy with which the interpolation matches this exact scaling at this level of truncation is remarkable. So what you can do then, okay, so this is P equals to 2/3. You fix that, and then you just optimize the value of lambda naught. This is what you get. You can see it's very accurate. And this comes from standard mathematical fitting functions. So if you plot now the values that the actual numerical values against this curve, you see that it's hard to distinguish any difference between the curve and the points. Now, this is very impressive. However, we need to remember this is for a given value of truncation. So the error that is likely to occur is the error associated with the truncation. So what we did was to run for an even larger number of loops for a certain number of coupling constant values, and then to estimate the error that takes that into account. So this is our final answer, and we claim to have this to within 3 significance. Okay, right. So you can then, so now we have a list of, I don't know, 2,600 and something correlators. So these are ground state time expectation values of correlators at the same time. But let's look at some typical examples. So this is a quadratic one, trace x1 squared by trace x2 squared over n squared. We do the same analysis. So I'm going to display these, but I don't expect you to actually try and understand every single point presented there. So all I've done is I've again take the log, find a fitting to what the value of p is. So again, we expect it to be minus 2/3. So that's very close. Plug it back, you fix p to be minus 2/3, and this is the final scaling function taking into account truncations. So this is, as you see, again, extremely accurate. You can do the same for quartic correlators. Again, it should be minus 4/3, minus 4/3. It's very accurate to plug it in, and these are the kind of fits that you get. Right. There is one comment that I want to make, which is normally if you do the integral, and this is done for 2 matrices, and I think this is part of the reason why possibly Monte Carlo struggles with masses that are 0, is that this is a Younger-Mills coupling, so you expect to have flat directions, where x1 and x2 commute, and actually it's becoming worse as the coupling constant becomes very, very large. But it turns out that this is an Hamiltonian system. If you look at this quantity, which is some kind of angle, right? It's the trace x1 squared, x2 squared minus trace x1, 2x. So if these were vectors, this would be 1 minus cos or theta. It's constant, and it's independent of the coupling. Okay. There's an observation, okay, that goes back to some work of Hartnell that I have mentioned. Okay, so at the time that this work was done, there were no similar numerical work for 2 matrices in the strict massless limit. In the meantime, Henry, Lin, and Zheng in July came up with they presented results, but essentially the work that I've done here with my students and postdoc was used as a benchmark for their methods. I mean, they call it a high precision bootstrap and so on. So this is how they compare it to some of the results that I've presented. So they have different conventions, but once you use the same conventions in both approaches, so my E naught of n squared. So by the way, they do it only for one value of the coupling. You know, once you expect the theory to indeed respect the scaling, that's good enough, because you can then scale things to get it at any other value. So this is what our work seems to get, 705. They claim that ground state energy is between, they give more precise limits, bounds. This is the trace of z dagger z, so the quadratic 2-point function at equal time. So slightly outside this. Level 4 operator, again, 0.38 versus 0.7. And there's a mention of some Monte Carlo work, okay, which is here. All right. So, yeah.
What end did Monte Carlo do?
Oof. Well, no, I just extracted that table from the results that Lynn. Okay. It's probably an extrapolation to some large scale, but yeah. But I don't know how high they go. Or not.
It would be large.
They could.
Usually why they do is yeah, 20 or something.
Actually, you did.
Yeah, well,
They put a master.
You should ask you what time.
the path integral is unstable because of that flat directions. So they put in a mass term and
So,
they
yeah.
send the mass term going to zero.
So that's normally the challenge, as well as taking extrapolating to larger. Okay. To my result, yes, I've noticed. Yeah, well, we'll have to wait and see. Okay, so there is something that this method does at the moment that Bootstrap cannot do. And that's the calculation of the spectrum. So as Antal has already mentioned, and I'm not going to give you details, but once you have the large N configuration, you can do small fluctuations and work out what the mass matrix is. Okay. It turns out there are a few technical aspects related to the appearance of a number of unphysical zero modes, but it's something that is well established, and I'm not going to give you details because as it is already running out of time. So what we observe is that the mass of the third excited states and all other excited states show the expected increase with coupling. Now, that's not the case for the two lowest lying states, but I'll discuss that briefly. So again, I don't want to bombard you with numbers, but just to show you the kind of results that you get. So that's the energy 3. Again, you expect P to be 2/3. That's how it comes out.
No, it's misleading. It should not be energy. This is omega. This is the frequency.
There's no frequencies that's
very different from energy.
masses. That's all.
Every oscillator gives you
Yeah, these are the.
So you should write omega.
Okay.
You write to claim.
Little omega. Okay.
You try to claim more states.
Yeah.
Every state can be multiplied.
Okay. Yes.
Huge number of states.
These are the omegas. Okay. So E3, E4, omega 3, E4, you see there's a doublet and then followed by a singlet. And then you see that comes, most of them come in pairs. Now that is to be expected because this theory if you were to change from, so sorry about that. If you, instead of having worked with emission matrices X1 and X2, I had complexified and had Z X1 plus I X2 and Z dagger, then this has a SO2 or U1 symmetry. So therefore, any state, let's say with charge L equals to 2, will have another one that should be degenerate with state with the charge L equals to -2. And that you can do, that treatment you can do. And indeed, that's what I show here. Okay. So this is log E, omega 3, 4, and 5. E3 and 4 from an L equals to plus minus to doublet. E5 is a singlet, and so on and so on. So this again shows, okay, not as accurate as you'd expect from the ground state energy, but it still very good fits to the states. The lowest lying states are particularly accurate, which are in principle phenomenologically more important. Okay. Right, so you wanted to know about masses. We introduced masses for a number of reasons. The one being that this is sometimes called the BMN, because the BMN is a mass that results out of compactification into S3. But also because there were numerical results available coming from the work of Hartner. So we compare it to that just now. And again, so once you introduce a mass, the behavior, strong coupling behavior remains the same, but then you have corrections that go like m squared over lambda to the p. So again, we worked in trying to get that coefficient. So this is how it fits into the strong coupling limit. Okay, I keep pressing the wrong one. Okay, so here are some comparisons. So this is the article for E naught over n squared. This is a work of Han, Hartnell, and Kruto. I think it's 0.8890. 0.882. And you see that the results are not too different. This is earlier work by Morita and Yoshida. So again, similar type of results. This is the 2-point function. Okay. And so Henry Lin and Zhang also considered a mass, and for a specific value of mass and specific value of coupling, they presented this comparison. So this is based on the bootstrap approach, and this is this work. You see this is much closer than massless case. Trace of Z, dagger Z, again very similar, and the level 4 operator also very similar. I'm going to skip this and move to 3 matrices. So we repeated the treatment to 3 matrices. So this is something that was published 2025. Again, I considered 9 values. I wanted to have a nice log dependence, so I have e to the -4 and so on. And in this case, I considered an even larger truncation, so Lmax was 10. That's 9,503 loops. And our capital omega is a 225 matrix. Typically, you put this into a Apple laptop, MacBook Pro, let it run for 2 days, 3 days maybe, and you get an answer. So it's not too bad. It works. So these were 69 by 69 matrices. 1 is diagonal, 2 are general. So what I wanted to emphasize here, so first thing so these are now, you have a long list of ground state expectations of products of operators at the same time. Anything that is odd should be 0, and it's 0 numerically, certainly to the number of significant figures that I'm showing you here. So these are the only ones that are non-zero. So that's the trace of x1 squared, trace of x2 squared, trace of x3 squared. So of course, there's a subgroup of O3 symmetry, which is the permutation 1, 2, and 3. We expect them to be the same, and this is what I wanted to display, is to show how accurate, to what level of accuracy they respect the O3 symmetry. 10 minutes, okay. Not too bad. Okay, so this is so there are no non-zero expectation values for any loops with an odd number of matrices. The next, you've got 1, 1, 1, so that a trace of x1 to the 4th, trace of x2 to the 4th, trace of x3 to the 4th. Again, you can see how the symmetry is respected. In other words, these were all treated as independent loops. And you have 1, 1, 2, 2, 1, 1, 3, 3, 2, 2, 3, 3. So again, there's just to exhibit the accuracy with which the O3 symmetry appears. And 1, 2, 1, 2, 1, 3, 1, 3, and 2, 3, 2, 3. Okay, so that's how they appear. Right. So again, the same treatment, or we fit the planar ground state energies to the curve V naught of n squared to some lambda to some power p. Take the log, perform a least square, fit to the logarithmic plot. In this case, you get even a more remarkable consistency check that p, that power there, this is lambda, is 1/3. But again, you cannot trust that to be nice, but that is that accuracy, because we expect truncations effects to be the dominant one. So that's an estimate then, with the best estimate taking into account the symmetries with which we find, for instance, the vanishing of odd correlators. So that's our statement for what E naught of n squared should be for this theory. Again, this is how the logarithmic linear fits and the predicted and the fits to the scaling dependence. Yeah, again, very precise. So So we did the same thing now. We've got a trace x1 squared, trace x2 squared, trace x3 squared. Again, we expect that to scale like minus a third. This is what fitting gives you. That means you then set p to be minus a third. And taking into account an estimate of truncation errors, that's what we did. Right. So again, some fits. Right, for 4-point functions. So I've got the structure that I call AAAA, which we take the 1, 1, 1, 2, 2, 2, 3 divided by 3. So these would all be invariant under permutation. So these are the 3 different types. So again, we expect this to go like lambda to the minus 2/3. That's how they come. And then this is the scaling function. Right, so logarithmic linear fits to predicted scaling. Right, so remember I had mentioned about, discussed briefly the issue of the, when you do the quantum mechanics, you don't have an issue. Any value of lambda with these flat directions. So again, we did the same analysis here. Or 1 and x1 squared, x2 squared minus trace of x1, x2, x1, x2. 1, 3, and 2, 3. And you see that again, they are pretty much constant and independent of that. Yeah.
Different.
Sorry?
Shouldn't the same all the angles?
So you expect A12, A13, and A23 to be the same, yeah, because if you have permutation symmetry, which is a subgroup of O3, and indeed that's how they, they're not 7909, 7907, 7909. So I'm happy with it. Okay. So again, we can now do the matrices, the spectrum. I guess here it's a little bit more interesting because this is 3 matrices, so this should be classified according to angular momentum. It has an O3, so it's the angular momentum quantum numbers. And indeed, so I'm showing you what I actually get for my omegas. The multiplets that come out of this analysis. So you have the lowest state is a singlet. I just showed for 3 different values of lambda. Please note that lambda equals to e to the minus 4 is extremely small. It's a massless theorem with an extremely small coupling constant, and somehow the system,
And what is E? Just
exponential. Yeah. So that's a very small number. Because I'm plotting logs, I decided for that approach that just take e to the minus something, and then it's nice in linear. Okay. Now, then you have an L equals to 2 states. You can see the degeneracy between E5 or omega 5 and omega 9. So then you don't have L equals to 1. And that's because you cannot form an anti-symmetrical L equals to 1 state out of 1, 1, and 1. Okay. Then the next is 1, 2, 3, 4, 5, 6, 7. So that's L equals to 3. And again, you see that the degeneracy is pretty much out there. You have to then look over the full range of lambdas to associate them, but you see that here it's pretty clear that these form an L equals to 3. Then there's another singlet. So indeed, they are coming out exactly, well, certainly as with quantum numbers that you'd expect from the addition of angular momentum. Okay, so I've done a little bit more than that. So a clear pattern of degeneracy is evident with the lowest mass singlet and a quintuplet corresponding to the traceless symmetric matrix. So what I've done here, I've taken the singlet, again, done the same analysis. This is an energy, should go like 1/3. turns out to be, even though it's the lowest state, it's not the most accurate. See that the other higher states are more accurate than that. But there's our estimate of the final scaling function. That's then quintuplet, okay? And here are the quantum numbers. And these so remember, this is a reduced model. So in this case, parity is trivial, is -1 to the L, but L is equal to J. However, the charge conjugation, one has to actually look at the eigenvectors. And it's remarkable that by looking at the eigenvectors, there is a clear indication of when you have negative charge or odd charge. Okay. So the first one appears here. It's a singlet. It's a singlet with plus and minus. Right. Phenomenology. I mean, of course, it's tempting immediately to compare with what people have done in trying to understand global spectrum using lattice gauge theories. So basically what we're getting out of this is that the mass of 2 or mass 0 well, two of the standard global states that people consider is 2. How does that compare? Quenched and unquenched SU3 lattice gauge theory gives you about 1.5. Some works that are found, well, they extrapolate to larger n, 1.68 to 1.74. But remember, these are not reduced systems. Well, I guess that's not too bad. Right. So what about more than 3 matrices, right? Because I think Anash wants me to do 9 matrices. And there we have a little challenge because this is how the numbers grow. So if you have d equals to 2, you've seen how the number goes up in all loops up to length less or equal than 8. 93, if you have 3 matrices, you got 1,000. But as you can see, I have 6,167,000 loops of length less or equal than 8. So is there a hope of doing anything about this? Well, one of the reasons why I showed you a transparency to exhibit the symmetry for 3 matrices under the O3 is to say, well, I shouldn't have to treat all my loops to be independent. If they're related by a subgroup of SOD, I should be able to treat them as having the same value. And in that case, indeed, and I worked out, you can see there's a drastic decrease in the number of loops. So for instance, for D equals to 9, now it goes down from 6 million to about 739. So maybe there's a hope of using this method to hopefully go to D equals to 9. Okay, so I think this is a summary of what I have done. Study the large N dynamics of 2 and 3 massless Young-Mills coupled matrix quantum mechanics by minimizing a loop truncated Levitsky-Sekita effective collective field Hamiltonian. Difference between this approach and that of the current bootstrap approach is that the loop space constraints are handled by the use of master variables. This is successfully applied directly in a massless limit for a range of values of the coupling constant, scaling behavior of different physical quantities are obtained with a high level of precision. We considered both planar properties as well as the large N ground state energy and multi-matrix correlators, but also the spectrum of the theory, which is a one-over-n effect. Finally, for the spectrum, I didn't discuss this in a lot of detail, but basically this is the trace of X1, the trace of X2. They remain massless, as you'd expect, because they decouple from the theory. If you have X1 to be proportional to a phase or a phase multiplying by the identity matrix, then it commutes with X2. So that's what you'd expect. And this is what you find But apart from those states, the advanced states develop with well-defined mass gaps. Okay, so open questions. So you may say, we should really be working directly in loop space while introducing these master variables, which are kind of the original variables, x1 and x2, which are n by n matrices. But if you are interested in somewhat other, this issues such as Eguchi-Kawai and stuff like that, normally what you have to do in order to reproduce the correct loop equations is you can consider 4 unitary matrices, but you have to quench the diagonal terms. So the fact that you're actually using the original x1 and x2 and x3, you can in principle implement that. Okay. So the next question, of course, would be BMN. Maybe you have 2 complex impurities, Z and Y, x1, x2, x3, and x4. Of course, supersymmetry I have not looked at. Need to try and then discover more, try to identify more gravity properties. I don't mention here, but I'm interested also in unitary matrices. And of course, of most interest would be then to consider finite. Okay, thank you.
Thanks, Joel, for the very nice one.
Questions?
Yes. So these are showing something like heat loss, EQ0. Slides, more.
Yeah, I have to go one by one. Yeah. Okay, so what I'm doing is simply working out the spectrum of the theory. Okay, so I have omega 1, omega 2, and omega 3 would be the first 3 ones. They are 0 numerically. The next one that's non-zero is E4. And then you have E5, E6, E7, E8, and E9 are the next 5 states. Okay, and they should be degenerate if they form an L equals to 2 multiplets.
Is there an emergence symmetry because it looks like all those states from E10 to E16 are same mass. The same for E5 to E9.
So I am considering them to have the same mass and that they form part of the same multiplet, in which case they should be, strictly speaking, degenerate. But it's true that the accuracy with which they are degenerate gets better for large number. That's what you observed.
So why is it dangerous?
It's what it should be. It's I mean, this is, you've got x1, x2, and x3, right? So these are the 3 components of an L equals to 1 angular momentum fundamental. You take 1 cross 1, you should get angular momentum 0, 1, and 2. So there's the, yeah, so 3 invariant. That's right. So this is the classification. So you have the L equals to 0, and the L equals to 2. You don't have an L equals to 1 because you would need to take x1, x2 minus x2, x1, or, but it doesn't allow you because you've got a matrix. Our coordinates are loops. Trace of x1, x2 is the same as trace of x2, x1, so you never get L equals. You get an anti-symmetric L equals to 1. But, all of them can be recognized as representations of O3, or angular momentum. And that I think is quite remarkable. Because remember, this is extracted from, these are the eigenvalues of an almost 9,000 by 9,000 matrix.
Yes, Costas. Maybe wasn't sure when you counted about, let's say, the 9 matrices you've got these problems of things. What's exactly the problem? Okay, I understand can it be run on the laptop, but can it be run on a cluster, or like is it can you use the same code you already have? And just need more power, or
In principle, yes, but I'm not Google.
no, but do you need like a supercomputer for that, or is that
I'm not sure.
Run on a decent size small
Okay,
cluster?
Yeah, I think even if you had a supercomputer, you would be limited. Whereas, I mean, I would struggle to have to minimize a system of 6 million with a matrix that is, I don't know, 500 or 2000 by 2000. It would be very slow.
So you need some new insights into how to.
Yeah, so yes. So the insights ultimately comes from dealing with the loop structure. See if you identify things. So my simple observation is if you respect the ab initio, the O3 symmetry or the discrete subgroup of O3, you may be able to do that. I should say that Henry Lin managed to give some results for d equals to 9, so which means he's able to focus on a certain number of loops without having to have the whole collection. Okay. On the other hand, he can't do spectrum. Spectrum requires the whole large N background.
More questions?
I have a question.
Yes.
That's probably the shuttle already.
I just really want to say your bus is here.
Okay.
Apparently
Yeah.
the bus was told to be here at past.
Yeah.
So he's happy to wait another, let's say 5 minutes or whatever.
Yeah,
He apparently has got a 6 o'clock pickup at the airport, and the traffic in Cape Town is notoriously hectic. So I'm just saying, you're welcome to either stay here. Huh? But yeah, I mean, you can, it's your choice. The bus is here for those that, otherwise it's really easy to walk. Also, Stellenbosch is safe, things are closed, so you don't have to take the bus. I'm just saying it's here. I can stall the guy a little bit.
5 minutes will be.
We are finishing.
Okay, cool. I'll tell him. Okay, thank you.
Yeah, that's